here, say, once you flip it, okay, so you can see that the OH, which is on the top, is going over there, okay, hydroxymethyl group, and then the O in the ring comes up. So this is very interesting thing to see.
Okay, should we move on to new material? So I'll switch out of that slide deck and get into the new slide deck today. We're talking a lot about pKa, acidities, basicities. We'll talk about how basicity and acidity relates to distribution of drugs throughout the body. And then we'll also move into some select examples. So the second half is going to be a lot of detailed examples, particularly in the realm of neurological disease. So how will molecules enter the brain or get rejected from the brain? So that'll be a specific subtopic for the second half. But first we need to lay down the basic principles. We need to talk about some of the basics about how compounds move throughout the body. If I can't reinforce it enough, we want to think very critically about the physical organic chemistry and understand how the physical organic chemistry relates to perturbing the properties of molecules, and then we apply that in the context of biological settings. Okay, so all these principles here that I talk about so much and spend a lot of time talking about are the foundation for understanding the distribution, metabolism, and pharmacokinetic properties that are still essential for drug discovery. Okay, so be a physical organic chemist first, and then apply that to the understanding of the science of the interface of chemistry and biology. So today, as mentioned, we're going to talk a lot about distribution of molecules throughout the body. And when we talk about molecules distributing throughout the body, these molecules typically need to get across membranes, whether they're going in and out of cells or across different membranes within the body that are made up of cellular monolayers, or whether they're circulating throughout the body. You need molecules many times to get through membranes. Sometimes you don't. So I'll pause for a second and say, be critical about your own drug discovery campaign. If you're dealing with topical antibiotics, you don't necessarily need that getting into systemic circulation and getting through into certain tissues, right? So you can be thoughtful and critical about the needs of your molecule, but right now we're going to be talking predominantly about systemically distributed drugs where we have targets that need to be accessed from inside the body. So this is what I call the zeroth law of drug discovery, drug design. It doesn't get mentioned much, but it's implicit for the process. So in order for a drug to exert pharmacological action, it actually has to get to the site, wherever the target is. Okay? It makes a lot of sense when you think about it now, and maybe we assume it too easily, but you can be more critical in thinking about it for your own drug discovery campaigns. It'll benefit you. So when we talk about distribution of drugs throughout the body, who knows pharmacokinetic modeling, compartment modeling for PK? Is this a new topic for most people? Yep. Okay. So when we think about, thank you very much. When we think about how molecules distribute throughout the body, we many times use compartment modeling. And what this is a way to model kinetically, pharmacokinetics, they're kinetics, right? To model kinetically where a compound is throughout the body. What's the concentration in different compartments of the body? When we talk about compartments of the body, we might have, you could define models with different compartments. You could have the brain or different regions of the brain. You can have systemic circulation going through the blood. It can get into fatty tissue. That can be a compartment. When you have an oral dose of a drug, the drug that's in the GI tract before it gets absorbed can be a compartment. The compartments can get more and more complex if you need more sophisticated modeling, but there are also very simple models too that can be developed. And again, something I think you'll see more in coursework as you move forward. Okay, so this would be a representative example of a compartment model in which we're looking at different strategies for dosing that drug. We might have an oral drug or an inhalable therapeutic, a spray that goes into the lung, and it's going to either go into the GI tract. Where's my laser? So it can either go into the GI tract there, If it's a pulmonary dose, that's going to be in the lung, right? So that compartment for absorption might differ depending on how we administer the drug. Now, in order for that drug to reach a systemic target, it needs to go from the GI tract or from the lungs into systemic circulation. That's the blood. And after it starts circulating systemically through the body, some of it might be bound to plasma. That can be modeled as a compartment. Some of it can go into fatty tissue or other tissues. That can be a compartment in these models. Who knows where the site of action is, where your target is distributed, but it might need to get into that specific compartment of the body to exert its action. Now, with this type of, and then we have compartments many times that represent the liver for metabolism and or kidneys for urinary excretion based on how you eliminate the drug. And these are, when we do these models, many times we're thinking about equilibria, so the compound can go into that compartment, it can go out of the compartment back into systemic circulation, and that happens as drugs distribute throughout the body. Okay. Now, in order for this compartment model to work properly, we typically assume the free drug hypothesis, and that's over here. So at the steady state of a drug, drugs can transverse membranes. That's not always true for all compounds, but it's an assumption we use for these types of models. Drugs can go back and forth freely across membranes. Okay? Now, additionally, we assume that there's a 1-to-1 ratio of drug across those membranes. Okay? Very simple model. And then the concentration of the free drug in the compartment where your target is exerts pharmacological action. Okay, all that makes sense. It's really basic when you think about it, but we need to be aware of the hypotheses and the assumptions that we have in our hypotheses when we're using these models. Okay, so really the key point for this lecture is that we need free passage back and forth across these compartments in order to reach the site of action. And many times that's going to require a drug to go across lipid membranes, plasma membranes. You've seen those phospholipids. This is a simple representative monolayer that I have drawn here. In reality, there are glycoproteins and other proteins embedded in these membranes. There are other challenges that molecules will face as they're trying to transverse. Nonetheless, if we have a drug and it needs to get across that membrane, that's really important for exerting biological action in many drugs. Okay? So that's what we're going to talk about today. We're going to talk about compounds getting across membranes. We're going to obviously talk about fluorination and how fluorination affects that process. It's heavily influenced by perturbations to the acidity and or basicity of the nitrogen and oxygen containing functional groups in the molecule. So there's an important perturbation we'll look at here. And again, log P is an important parameter when we're thinking about distribution. And log P is something that I think most people have been introduced to early in coursework. Just a brief reminder of what this is. Log P is a distribution coefficient. It's the ratio of drug that will predominantly exist in octanol versus water. So it's a shake flask method that's used classically. You take your compound, you put it in this octanol water layer, you shake it up in like a separatory funnel, you measure the concentrations on both sides. And if a molecule is greasy, it'll tend to reside in the octanol layer. If it's more water soluble, it goes into the aqueous layer, and that ratio is important for drug discovery. Okay, because when we think about this process of a drug being solvated, when it's on either side of the membrane, it's surrounded by water, it's solvated. The nitrogen and oxygen containing groups are typically hydrogen bonding, either as donors or acceptors with water. But in order to cross the membrane, you need to dehydrate. They're not going to pull water across. Okay, you need to be in a neutral form to get across. And in the membrane, in that layer, that's all grease. So you need to have sufficient solubility in a greasy environment to get through the membrane, but then you need to be sufficiently water soluble when you get to the other side. So one of the reasons why you need a balance in this lipophilicity parameter. It needs to be soluble enough in water so it can circulate throughout the body, but also needs to be greasy enough to make it into the membrane. Okay, so it's a balance of those properties that we're looking for, and the ratios are used in these equations, log P and log D. The difference is in the pH at which these are measured. So when you do these and just put the compound into water itself, That's what we call log P. That doesn't necessarily represent physiological pH. So we use a log D at pH 7.4, and that's where we use a buffer at pH 7.4 so you can account for ionization states that are going to occur in a physiological system. So if you're going to be cationic or anionic because you have acid or basic moieties in your molecule, log D represents the solubility and the two layers better, okay? So we have log P, log D. In the literature, sometimes you see one, sometimes you see the other, and the difference is the pH at which they're measured. Cool? Basics. I know this is, a lot of people have seen this before, but I just want to make sure we're all up to the same page. So optimal log P values based on maybe where your target is throughout the body, what your route of administration is going to be. If you're going to inject a drug straight into systemic circulation, like an IV injection, that can be a compound that's super water soluble. It doesn't need to be lipophilic to make it across like the GI tract. It can go straight into the bloodstream just fine. In contrast, if we want an oral drug or a drug that gets into the CNS, we might need something that's a little bit greasier there. If we want something that we're going to use like on a patch or a cream or an oil that we put on top on the skin and want that to distribute through the skin and through fatty tissue on the outer, near the surface of your body, we need those to be really, really, really greasy molecules, and log P can be higher in those situations. So you need to know your therapeutic class, where your target is, and then you can establish a drug product profile, what you're shooting for. And then we can start addressing, is our compound likely going to be greasy enough or too greasy? But there is a little bit of thought in developing your target profile before you move into trying to identify an appropriate log P range. Okay? Okay. If you get too water soluble, you might not get across membranes. But if you have too much lipid solubility, if you're too greasy, and that's a high log P number, you typically face several problems. Number one, you get buildup of drug in fatty tissues. That's a challenge, that's a problem. You might not get to the site of action if the drug is just sitting in fatty tissue. You might have excessive metabolism. We'll talk a lot about metabolism, but drug metabolism predominantly involves oxidation, or one phase of drug metabolism predominantly involves oxidation of grease that facilitates clearance of the drug. And then you can also have drugs that are too greasy, and instead of going through the membrane, they actually just go into the membrane and they sit there. And they don't come out the other side. And that can be a problem if you get a drug that's too greasy. So there are several issues with having compounds that are too greasy. Many individuals will say log P greater than 3 is like undesirable for those three reasons. There are drugs outside of any rules. So even Lipinski's rules. Do we know Lipinski's rules? Everyone knows Lipinski's? Okay, most people know Lipinski's. So there are outliers to Lipinski's rules. There are plenty of them. Okay, so for any of these trends, you can have outliers. Okay. So let's start talking about details of how fluorination can influence lipophilicity. This is actually like the topic that drove my interest when I was a grad student and brought me into organofluorine chemistry. Like it's on this slide right here. Okay. So everybody talks about how fluorine increases lipophilicity. And if you stop and think for a minute about what you're doing, if you put fluorine on a molecule, your carbon-fluorine bond is highly electronegative, it's a strong dipole, and if you add a strong dipole to a molecule, wouldn't you think that would increase water solubility? Doesn't that make sense? But everybody says it goes the other way. Okay. And so that's the question when I was, in 2005 or 2006, when I was writing a proposal for my graduate school. We had a requirement that you had to write proposals in graduate school. And that was like the fundamental question, like, what the heck is going on here? That can't be right. That's not true. Why is it, if it is true? Okay. So I'll start to explain that there are different situations depending on where fluorine is introduced on your molecule. It can either increase or decrease lipophilicity based on what's in the vicinity. And then we can understand the perturbations and the why, and then you can use that in your own discovery campaigns. So let's get into the actual data on this slide. So we have it aligned such that we have non-fluorinated compounds on the left and we have fluorinated compounds over on the right. So that's the big picture organization. You can see the log p values that we're going to compare horizontally between matched pairs. So if we look at that top pairing, you have alkyl systems on the left. You can see the log p values, 1.8 and 3.1. If you add fluorine atoms, individual fluorine atoms to those species, exactly what I mentioned before like what should happen, happens. You introduce a CF bond, you introduce a dipole into the molecule, you increase water solubility, you decrease lipophilicity. And you can see that in the numbers. Look at the magnitude of the difference, about 1 p unit. This is a logarithmic unit, right? So a change of 1.0 is a 10-fold change in the ratio. Okay, so these are all log units. And then, just 0.8 log unit difference there for the slightly longer derivative, okay? So if you have an aliphatic system, no heteroatoms, you put a fluorine atom in there, you increase water solubility. Not what people always say. So let's dispel that myth. It depends on what's in the vicinity of the fluorine as to whether you get an adjustment upwards or downwards. So in the next series, we're going to look at a series of alcohols. You can see ethanol, propanol, and butanol over on the left. And in this series, we're adding a CF3 group at the terminal position of all of them. And here is where you start seeing the increase in lipophilicity. Okay, the magnitude of that, you can see a change of 0.6 log units roughly when you go from ethanol to trifluoroethanol. It's more lipophilic. The magnitude of that change is minimal if that CF3 group gets further and further and further away from the alcohol. So there's something about the distance between the heteroatom, the oxygen, and the CF3 group that's really important for understanding this property. Okay, look horizontally here. We have a 2-carbon spacer, and you see nearly the same number, and same thing down here when you have a 3-carbon spacer, basically the same lipophilicity. Okay? So there's something about the distance between the atoms there. And then if the linker becomes too long, we go back to the original effect that we're introducing fluorine and improving water solubility relative to lipid solubility. You see that here. Now we have a 4-carbon linker between this matched pair, and you see the lipophilicity goes downwards. And same thing over here. Now we have a 5-carbon linker, lipophilicity goes downwards. Okay. So the perturbations experienced by the oxygen will be, the perturbations in whatever the CF3 is doing are going to be felt when the CF3 group is close to the alcohol, but not as it gets too far. Cool? Makes sense? Okay. So this change in lipophilicity, the use of fluorine to make things more water soluble can be really useful for various reasons. We'll see some issues with metabolism addressed by this type of property tomorrow. But it can also decrease lipophilicity when used intelligently and systematically. So this is a nice slide from David O'Hagan's. Well, the slide is great. It's my slide. It looks great, right? No, it's a nice study by Dave O'Hagan in which they're looking at lipophilicity of a series of compounds, and this is biphenyl and cyclohexane, phenyl cyclohexane here, pretty greasy molecules. You can tune the lipophilicity, make more water-soluble compounds by patterning the fluorine. So you can see the syn arrangement here, the 1,2 arrangement. Look at the magnitude difference in that matched pair right there. Remember, those are log units, right? 1.5 log units is a lot there. We can put another fluorine atom in, further drive it downwards. You can see that the stereochemistry of the fluorine has a little bit of an effect there. So that's interesting. If you have this one, what would this be? A 2, 3, 4, 5 phenyl cyclohexane, all syn. Look at how much we've driven water solubility, right? 2.5 p units, that's a lot. And what's going on in this case is that we are actually improving the interactions with water. Right? In order for something to be water soluble, you need a hydrogen bond with water, either as a donor or an acceptor. And in this case, the fluorine atoms, being sigma withdrawing effects, make the axial hydrogen atoms on the bottom face acidic. And when they're acidic, they can hydrogen bond with water. The lone pair of electrons on water being the acceptor, the acidic protons being the donor. Okay, you can use it strategically. This is a fluorine-induced perturbation, and it's due to the strong sigma withdrawing effect of the fluorine atom. Okay, the electronegativity effect. Make sense? Really cool example here of fluorine when patterned properly on an aliphatic scaffold can drive water solubility so much. Really nice example. And this can be combined with other substitutions that also improve water solubility. So it works if you have other hydrogen bond donors or acceptors in the molecule. Here's a series of anilines. We don't always want anilines in drugs. You have other oxidative issues when you have anilines in a drug. Carboxylates, you find those on some drugs. But the trend that fluorine patterning can drive water solubility also works in these other settings. Okay? So we're going to see how these types of substitutions affect metabolism in the next lecture. And as medicinal chemists, you always want to be aware that when you're trying to change one property, there might be other changes also going on in your molecule. So you have to be able to track all these different parameters. So even though we're trying to influence lipophilicity, what's it doing to metabolism? What's it doing to any of the other metrics that I'm using to track my molecule? So you want to have this like multifunctional processing unit in your head to be able to track everything there. So that was aliphatic systems. Okay, in aliphatic systems, if you fluorinate, it's strictly aliphatic. You start fluorinating and you fluorinate intelligently, you can drive water solubility. So in the next series of examples, we're going to talk about aromatic systems that are extremely common in drug discovery. Plenty of arrow rings and heteroarrow rings in drug discovery. Well, if we start introducing fluorine onto those, what happens to lipophilicity? And that's what we're going to look here. And when we look at these, we use a pi parameter. Pi is a parameter used for linear free energy relationships, which you've seen in physical organic chemistry. And it's basically looking at the logarithmic, at the log of the difference in log p, between benzene and whatever your substituent is. Okay, so we're looking at a delta log p when we say pi parameter. And so we'll just look at a series of these with benzene being the 0 point for this analysis. A single fluorine atom increases lipophilicity barely. 0.1 units, 0.15 unit, not too much there, but there's a little bit of an increase. Just for comparison, if you put a chloro substituent on there, 0.7, that's a greater magnitude. And if you think about a methyl group, that's a half log unit. So if you put a fluorine atom on there, there's a minimal change, but not too much. And that change goes the opposite way of what we saw in the aliphatic system. In the aliphatic system, we lower log p with a single fluorine atom, and in an aryl system, we increase log p. Okay, so what it's attached to matters. Now, we can go ahead and take the methyl versus CF3 example and compare those and recognize that you get a further increase in log p when you fluorinate benzoic position. So the benzoic position going from 0.56 to 0.88 is definitely an improvement. But when you think about the magnitude of the change per fluorine atom, it's not very much. Delta log p between these two here, you can do in your head really quickly, right, about 0.3. And that's not much when you have 3 fluorine atoms. Each fluorine atom is like 0.1. So you're not getting a huge change here on these simple model systems as you fluorinate directly on the ring or on the benzoic position. Little change, but not all that much. Now, if you start fluorinating further away on the regular aliphatic system here, then you see a bigger change. And again, that's an ethyl group. So we go back to the paradigm that we saw right at the beginning, that we're just fluorinating on like a regular aliphatic system as you get away from the ring. Okay? So you can keep those in mind. As we continue to walk through, what we'll realize is that when you fluorinate, adjacent to heteroatoms, you get huge perturbations. And we started to see that on the first slide. Okay, as we had our ethanol, propanol, butanol series, and we saw the magnitude of the effect was great on ethanol and less and less and less as you move the CF3 further and further from the oxygen. Now we have the CF3 attached directly to the oxygen, and the delta log P there is about 1 unit. And I'm looking at these two over here, the anisole versus the trifluoroanisole there, 1 log unit, big change. So how would you explain that? What drives water solubility? Hydrogen bonding with water. So what is CF3 doing? Let's just start with anisole. With anisole, what's engaging water? Dipole, and we also have lone pair of electrons.
So the kind of hydrogen bonding, I mean, that is being hydrogen bond acceptor, and water is donating the hydrogen.
So you have a donor-acceptor interaction, like the OH, the H is the acid in this interaction, and the oxygen is the base in this interaction, the lone pair of an oxygen. And if you fluorinate, what happens to the basicity of the lone pairs on oxygen? Decrease, right? The sigma withdrawing effect between the CF3 and oxygen starts pulling electron densities toward the CF3. Oxygen, as a result, kind of retracts its electrons a bit. They become less basic, less engaging with the water. 1 log unit difference between in that matched pair. Right? Makes sense when you think about it? Okay. So we can keep going on. The same is true if you have other heteroatoms here. If you trifluoromethylate thioanisole here, you can see a significant difference there. Not quite as much, 0.8 units, but that's still pretty significant. You can see you have sulfones, you get a big change there. Again, the perturbation is through a couple of atoms, but in the SO2 group, it's the oxygen atoms that are basic and engaging water through hydrogen bond donating, accepting interactions. And that CF3 group, again, forces the retraction of those lone pair electrons. They're less basic, less nucleophilic. Okay. So there are more and more examples. I think we've walked through in detail enough, but you have more examples on your slides, and you can look up these parameters also in various texts and references. There are some lists you can find online if you want a comprehensive version of these TAF parameters, but I've just selected, the pi parameters, but I've just selected a subset of match pairs from fluorinated versions, okay? So there are other common substitutions that we encounter in medicinal chemistry. This table looks like a lot, and we're not going to cover in detail every single example. I'm going to summarize some general trends. It's common to take a hydroxyl group and replace that with a fluorine. Now, sterically, this is a pretty reasonable change. When we started on day 1, many of the steric parameters for a monofluoro group were similar to the oxygen. Like this was like the very first slide, lots of data on it, looking at bond lengths and the size of the atom. So this is an isosteric replacement. It's pretty distinct because you have a hydrogen bond donor here and nothing there. Okay, so you're definitely going to get different properties. I'll explain a couple of general trends. If you have electron withdrawing groups on your ring, there's a reasonably modest effect across the board. You don't seem to perturb lipophilicity greatly. But if you have electron donating groups, you do see a significant perturbation. Okay, so it's a general trend. There are a lot of details and nuances within the data. But I think it's a good exercise for individuals to think critically about why. Okay, so I'm gonna leave that for something to go home and think about. Maybe after you think about it a bit, we can come back like in the next class, like right at the beginning, the first 2 or 3 minutes, and look back at this and see what you all think about that. Okay?
I'm particularly interested in that when difluorinated, difluorine functionalized aromatic ring. So you see that in the para position, so you have the delta log P, that is
Mm-hmm.
0.36, but in the ortho position, you see there's a, I think that's significantly big, right? 0.6.
Greasier? Yeah.
So basically ortho position, if you have a fluorine OH or a fluorine fluorine, then the log P, if you change it to fluorine fluorine, the log P changes more. That means it becomes more lipophilic as compared to what it would be in the OHF. So what is the reason? Because that's OH was, of course, OH was doing hydrogen bonding with water.
Mm-hmm.
But in this particular case, this change is much bigger. In the case of ortho.
Yeah, I think it's a really good question, and I haven't thought about that pairing yet. As I was going through and preparing this, I'll have to think about that more. You know, it's the delta, right? The difference in this series here, but it's not just which one is the most. This is a change in lipophilicity, which is a bit trickier to think about. Yep, yep, yep. I don't have a great answer for that right now, just off the top of my head. It's a good one. Another substitution might be a methoxy group for a fluorine atom. In this case, you have hydrogen bond accepting capability here. And maybe, it's pretty weak here, not very good. But you don't have the hydrogen bond donor. And when you have this type of situation, things are all over the place. You do not have consistent trends. But most of these perturbations are reasonably minor. Okay, so this substitution is reasonably isolipophilic within a little bit of error. The magnitude of the changes rarely get up to half unit. Most of them are less than 0.2 or so. Okay, so these are pretty minor changes, and you can get away with them without causing too much of an issue with changes in log P. Okay, so that's the main story here. These are reasonably close to each other in terms of lipophilicity. You can make these changes on heterocycles. The manuscript I have here has a wide variety of additional examples that you can dig through of increasing and increasing complexity. So if you want to see real-life examples of therapeutics and candidates, you can see that. When you fluorinate in the vicinity of heteroatoms, you get the bigger bang for your buck. Okay, so that's where you get this massive change there. As you get away from the heterocycle, that change drastically it falls away. So you can see the magnitude of the changes again on the heterocycles. If the fluorine atom is further away from the basic moieties, you see a minimal change. Okay. Questions on these ones?
So if we compare the trimetoxyphenol that we have already seen, that
Trifluoroanisole.
yes.
Yep.
So in that case, the lipophilicity was decreasing, right? But in case of that pyridine,
Coming over here?
yes.
This example here? You said is this the, is that what you're talking about?
Earlier one.
Earlier?
At the dipole, here itself. So lipophilicity is increasing, right?
Yep.
But in case of that pyridine, what is happening? That I want.
Yeah, so the pyridine has a really strong hydrogen bond donating and accepting potential because you have an acidic proton. The O has basic lone pair of electrons, and nitrogen has basic lone pair of electrons. When you make this substitution, you lose the hydrogen bond donor and acceptor, and you also minimize the hydrogen bond accepting ability of the pyridine through an inductive effect. So you have multiple things that are changing all at once with one substitution. So there's a lot going on in this example. Yep.
So in the previous slide, like when we are replacing in those tables, like CF3 is like decreasing the lipophilicity as compared to CHO and CN, although like CF3 also has
No, so these are not, you're saying, are you trying to compare these values?
Like fluorine versus CF3.
Right. This one versus this one? So you can't actually compare these values because this is delta log P for a matched pair. So it's the difference between the phenol bearing this versus the fluoro bearing this. And so you can't do a full match, like you can't compare this number to that number, I don't think, directly.
The ortho position, the fluoro group, that can be explained to hydrogen bonding. If that fluoro is engaged with hydrogen bonding with OH, that time it will be that lipophilicity will be high. But if in case of CF3, that hydrogen bond we cannot, maybe not possible, which decreases its intra-hydrogen bonding, not inter. So that increases its lipophilicity, decreases lipophilicity.
Yeah, so delta log P would be greater here because it's intramolecular hydrogen bonding interaction that's being disrupted or introduced depending on which way you're going. And it, yeah, I'd have to think about it. There are some, that's a complex topic. Who did that? There's a series of studies looking at phenols and benzyl alcohols and the intramolecular hydrogen bonding differences with like exactly these types of questions. I can go look up the name in the break, and there's a series of papers looking at those types of things. Yep.
Yeah, like because he brought out this point, because you just mentioned about the pyridine example, orthofluoropyridine and orthohydroxypyridine. So something very similar is happening in this example also, because now we are comparing orthofluorophenol versus the orthodifluoro. So with the difluoro is now removing the possible hydrogen bond donor acceptor capacity, the OH is gone, and plus it is also affecting the hydrogen bond capacity. So I think that also a little bit explains, similar to like pyridine case, that increase, that 0.665.
Okay. So we can also look at other substructures, other common perturbations in drug structures might involve the replacement of a hydroxyl group with CF2H. As we'll learn in Friday's lecture, CF2H can serve as a hydrogen bond donor. So the two CF3 groups, sorry, the CF2 group, the fluorine atoms, through an inductive effect, acidify the geminal H, and that can then serve as a hydrogen bond donor. Okay, so this substitution of an OH versus CF2H is used sometimes. There are different estimates about how strong of a hydrogen bond donor it is, so it varies based on what type of a metric you use, but there's the capability of doing that. The second substitution that we'll look at is going to be a methyl group versus a CF2. And we'll start to walk through some of that data really briefly. In the first case, as we look through this series, the OH to the CF2, that's on an arrow ring here. So the OH versus CF2 increases log P, and that makes a lot of sense because the CF2 doesn't have basic lone pair of electrons. Okay, it can't hydrogen bond with water very well through as a base. And in contrast, the phenol can, right? The phenol has an acidic proton and it has lone pair of electrons on oxygen, so the water solubility is going to be better there. And you see that in this series. In the second series here, we're replacing a methyl group with a CF2, and we do increase water solubility. In some cases greater than other cases, but overall you see changes there. When we come into the second series here, we're going to look at ethers and sulfones and do the same comparison. So if we have it, in this case, the group directly attached to an oxygen, we're not looking at peroxides. We don't use those in drugs, right? So we can't do these ones here, but we can go ahead and look down here and say, what if we have a methyl ether in an aliphatic system relative to a difluoromethyl ether on that system? And you see a big 1 log unit change there and a 1 log unit change when you look at a like methyl sulfone compared to a difluoromethyl sulfone. Okay, so you can again get reasonable perturbations in lipophilicity. In this case, we still use the same explanations that we're perturbing the nucleophilicity or basicity of the lone pair of electrons on the heteroatoms that are in the direct vicinity. And that's the reason why we improve lipophilicity in these cases. Cool? Okay. So you have to look around the molecule, and when you're putting fluorine in, are you closer to heteroatoms? Are you making perturbations there? Are you an aliphatic system? And then you'll get a better feel for which way you're likely going to drive lipophilicity. So in the next series of compounds, we're going to talk about the acidity and basicity of acids and ethers. Yep.
When we take break for how long?
Yeah, so is this for tea?
Yeah, I just want.
Okay.
Half an hour.
Give me a second here. Where's my cursor? Yeah, we'll go 25 minutes. 25 minutes. Okay, there we are here. So let's come back here, and we're going to talk about carboxylic acids. We know about carboxylic acids in general. There's a common reagent we use, TFA, deep protection of Bach groups, and other transformations sometimes too. We say that's a pretty strong acid. It's a sigma withdrawing effect as you take, in our model system here, just acetic acid, and start adding halogens. You perturb the acidity and increase the acidity, and that increase correlates with the electronegativity, right? So that more electronegative elements, as we add iodine, bromine, and then fluorine, increase the acidity. And again, that's just the inductive effect that we use to rationalize. And that's additive, so as you add in one fluoro group, two fluoro group, three fluoro groups, you see this sequential increase in acidity, and it can be pretty powerful because relative to acetic acid, we've changed over 4 log units, over 10,000-fold more acidic. And we can see that when we look at some other heteroatom base groups also. And then you can also pattern fluorine around aromatic rings and perturb the acidity and basicity of the atoms that are attached to the ring. So this is a benzoic acid that we're looking at, and a perfluorobenzoic acid, and you can see a pretty substantial change in the lipophilicity, sorry, in the pK of those species. The same is true with alcohols. Now we're going to start rationalizing the data that we saw on the initial slide and really connect the log P from the first slide we covered, the changes in log P, we're going to connect them to the acidity and the basicity. And it really is the basicity that tracks most critically here. The basicity of your oxygen and nitrogen heteroatoms that really drive the water solubility and the lipophilicity changes more than the acidity term. Okay. So let's look at this series of alcohols. We already saw ethanol and trifluoroethanol there. You can see the pKa change. Look at that change. Over 3.5 log units there. The acidity, that's alpha. You can see the definition of it right there. So the acidity, the donating ability, our acidity is there. The donating ability is here. The donating ability is a hydrogen bond donor, allowing that hydrogen atom to increase. The CF3, being more acidic, allows that hydrogen bond to make better interactions with water, perhaps. It's more acidic. It's a better donor. But the basicity of the lone pair of electrons on oxygen are stronger for ethanol relative to trifluoroethanol. Okay, and this is a really critical data point here. These are measured values. The basicity is higher. The basicity of the oxygen is what makes the hydrogen bonding interaction with the H of the OH, right, of water. Okay. So the main perturbation here is really the change in the basicity of the lone pair of electrons that drives the changes in log P, more than the acidity term does. Okay. And the same is true as you look at further and further down this chain. There's a series of alcohols here, so we can look at isopropanol and HFIP here. Big change in log P, perturbation in the hydrogen bond donating capability, and the accepting capability. Again, the accepting capability is what really drives the change in lipophilicity here. It's a loss of water solubility that really drives it. Yep.
So, okay, the alpha is the hydrogen bonding donating ability, beta is the accepting ability. So, hydrogen bonding accepting, this is the base, right? So, we see in these two cases, the one you are currently highlighting and the other one, that the basicity is increasing because H bonding accepting ability is increasing, right?
I wouldn't say it's because. I mean,
Okay,
but yeah.
that's okay.
Yeah.
No, but then the other side, when I look at that alpha values are decreasing, right? So it's not a good H bond donating ability, which means yeah, it's not a great acid.
So it's less acidic.
Less acidic, right?
Right. So that means that the acidity is not what's really driving
Okay. No.
the changes.
Because I was correlating with the pK value. No, it's fine.
Yeah.
It's fine.
Yeah.
pK value is decreasing because even though it is not that acidic, the pK value is pretty high. It's actually in basic range of the the conjugate the bases.
Mm-hmm.
So yeah, so that's okay. It's dropping marginally. Yeah.
Mm-hmm. Okay, so the same can
But I think that had you put it in pKb value, then beta 2 we could have probably correlated well. But that's
Yeah.
okay.
Yeah.
This is understood.
Yeah. Okay. So again, there's more examples and to dig through. The trends are generally the same. Yeah, we had another question.
One more question is that regarding carboxylate, right? So if we compare the pK value of methylene iodide, methylene bromide, methylene chloride, and methylene fluoride, right? Yeah, right. So how we can compare the pK value? Like the more the carboxylate ion will be stable, lesser will be the pK value, right? So in case of if we compare the CH2I and CH2F, so the pK value of CH2I is quite means higher as compared to CH2F.
DR? Yep.
But iodide.
But it tracks with electronegativity.
Iodide is not a means too much electronegative than fluoride. Fluorine is.
No, fluorine's way more electronegative than iodine.
Fluorine is more electronegative,
Yeah.
right? So.
So what we have is increasing electronegativity.
Right.
And then increasing acidity. Yep.
I got confused.
Okay, it's all good. Okay, so there are a couple more examples. The trends are generally the same. The key here is that it's the basicity driving the water solubility, and that's where you get, when you perturb the basicity of the heteroatoms, that's where you see the big changes in lipophilicity. So yeah.
Yeah. So I just had one question because I was thinking about planning some of the work what we are doing in the lab based on this data. Very interesting data. So these are all the values are the real values, pK and log P values, are the computational values. Or how much they correlate?
I don't recall if these are computational or experimental from when I pulled this. I probably made this part of the slide deck in 2017, 2016, and I don't remember exactly.
My point was asking was that how much they correlate, like if there is a real values and computational values, so that we can prepare a set of like all possibilities what we are expecting and then plan the synthesis.
Yeah, I think that's something to, as you're applying it in your own, I mean, we can look back at the resource and find a couple of the original references too and figure that out. Yep.
Yeah, because in our discovery process, like some molecules, we want to improve the pK or at least the solubility because the target receptor is inside and it has to pass the outer membrane. So maybe improving the solubility might help. Right now we are not in set up with PK studies, but at least I was thinking that we can use the computational values and then plan which modifications we should do.
Sure. Yeah. We can discuss details. So these trends are also, they also correlate with drug-like structures and cyclic systems too. We'll come and start talking about cyclic systems a little bit more later when we talk about amines. Nonetheless, you can see changes in pKa and eventually log P as you fluorinate, and as you rotate the fluorine atom to different positions, you actually see different perturbations. Okay, so the closer you get the fluorine to, in this case, the carboxylic acid, the more powerful the effect is relative to when you rotate the fluorine atoms further and further away. Okay, and that's true in both cases. We have a case where we have a carbocyclic scaffold and an ether scaffold. And as you go from the carbon-based system, again in this data, to the difluoro, you see you see changes in the pKa of your groups. Okay. Cool. Good.
What was that one in the packet and what is the difference? 3.81 versus 2.5. Acha,
Log P and
okay,
PK.
sorry, I missed it.
Yep. Sorry, I think I mentioned it, but didn't point at it. So pK and log P are both on that. Yep. Okay. So let's talk about just a couple of other functional groups. You don't necessarily see ketones very commonly in drugs, but we'll talk a little bit about some specialized ketones in the very last section, like one of the last couple of sets of slides. And so the perturbations are still relevant. The perturbations in basicity are relevant for carbonyls. So if we have acetone and trifluoroacetone, you can see a pretty profound effect in the basicity of those lone pair electrons, as shown here. In addition, you have the perturbation of the acidity and basicity of amines. And the perturbation on amines is like one of the most impactful things in drug discovery. So if you can perturb the basicity of amines, you can change all types of properties. And you'll see some more of that in the second half of the lecture. So if we have an aliphatic system, just ethylamine versus trifluoroethylamine, you get a huge change in pKa. And that change is super, super, super important because you can take an amine that's typically cationic under physiological conditions and make it neutral. Okay, so physiological pH about 7.4 in normal tissues or in plasma. We can take a basic amine here, typically protonated, pKa of nearly 11. That's going to be near fully protonated. And look at that pKa, it drops down several log units. It's below 7.4, it's below 6. Now we're neutral. And you see a change in the basicity of the lone pair of electrons on the amine also. Look at that change, much less likely to engage with water as a hydrogen bond acceptor. Okay? It's going to change log P pretty drastically. And the same thing can happen on anilino systems. We can perturb the pKa of the aniline pretty drastically if we pattern fluorine properly around the ring. In this case, we're looking at perfluoroanilines. There's 5 fluorine atoms, but you would still see an effect of lesser magnitude if you only had a couple of those fluorine atoms. Okay? So really important things to look at and think about. These changes, again, can be seen in carbocyclic systems. The perturbations here going from non-fluorinated. You can see the data, the pK and the log P. These are pretty profound changes when you're dealing with amines. So we have the carbocyclic systems in red, the ether system is in blue, and you see as you introduce the gem difluoro group a couple of atoms away, alpha, beta, gamma, so that's the gamma position. You can see a significant drop in the pKa and the lipophilicity. That one should actually go up a little bit, so that's 1.69. If we rotate it even closer in here, you see a further perturbation in the pKa and the acidity of those. Okay, really important, really valuable for drug discovery. In both cases, this would be half protonated at physiological pH. This would be not protonated at physiological pH. Okay. So there are algorithms for predicting, just on the back of an envelope calculation, you can predict the perturbation of pKa with a really simple system here. You don't need sophisticated computational methods to do a quick estimate. Okay, maybe you need to do those for your project, but you can also do a quicker estimate this way. What you do in the system is you identify the distance between the amine and the fluorine atom, however many fluorine atoms you have in your molecule, identify the distance. And we talk about distance for this chart. We're talking about distance in Greek letters, so alpha position, beta position, gamma position, delta position, right? So that's the way we count in the system. And then the perturbation based on the distance is shown here, the delta pKa. Okay, so you have one fluorine atom, beta, think about minus 1.7 units, gamma, minus 0.7, delta, epsilon, you can see those values. The magnitude of the change decreases as the distance increases. So here's a couple of examples of how you would use it. You take the known pKa or calculated pKa of your amine. For a cyclic system, we actually have two paths that we need to follow. This is a single fluorine atom, alpha, beta, gamma, to the gamma position, but it has two different paths, so we have to actually count both of the paths. So the perturbation in this case is path 1.7, but also path 2.7. So you would anticipate a change of minus 1.4, and this is, for a quick calculation, 1.7 is pretty close, minus 1.7. If we rotate it over, now our chain length changes, right? And so we have alpha beta. The beta is minus 1.7. When we go the other way, that's going to be a delta, and so we have a change of 0.2, and it's minus 0.8, or 1.8, okay? If we have two fluorine atoms, 0.7, 0.7, 0.7, 0.7, we get a change of 2.8 pK units, negative change, and experimentally 2.6. So there's a little bit of error with these calculations, but it's an initial estimate that you can use. Okay? We good with using this for quick estimates? Okay, so let's start putting more and more and more together and think about how this applies in real life systems. I keep coming back to this figure here. In order for a drug to cross a membrane, it needs to go from a hydrated state to a dehydrated state. Now, this dehydration does not necessarily occur in solution, in plasma. Okay? Many times this dehydration occurs as the molecule is passing through the membrane, so the greasy part starts going into the membrane, and then the water falls off as the molecule continues to go in. So recognize it's tough to draw that process on a little 2D slide like this, and then it'll rehydrate eventually once it gets through the other side and it comes out the other side of the membrane. Okay. And log P, as we look at the data, is the ratio of octanol solubility relative to water solubility in that shake flash method, and that mimics whether the molecule is going to be happy enough in the greasy environment in the membrane, and if it's water soluble enough to come out the other side properly. Okay. Now, fluorine perturbs the acidity and the basicity of the heteroatoms attached to the drug. So it'll make a more acidic hydrogen bond donor a less basic hydrogen bond acceptor, and we typically correlate the changes in lipophilicity with this property over here. We walked through that, but I just want to come back to the main big picture here. The main effect of fluorination on lipophilicity comes to perturbing the basicity and then the engagement of water here. I said it a couple of times, but I wanted this picture to be bold and in your face so you can think about this as you think about molecular design and drug discovery. So let's look at a couple of examples now that we've looked at a lot of data and a lot of model systems. Now we can actually start looking at drug structures. This is the one that we saw yesterday. And so this is an example of a serotonergic agent. The binding data here is typically in nanomolar for this series. The initial lead compound is basic. This nitrogen is basic, pKa of nearly 10. It's a reasonably potent compound, but poor oral bioavailability. Mainly because that amine is cationic under physiological conditions. If you have a plus charge on your molecule, is that going to get into a greasy membrane and be that happy? That plus charge is going to be reasonably hydrated. So in order for this molecule to pass into a membrane, it needs to get into a neutral state. And for it to be neutral, we can adjust the pKa, the basicity of the amine, using fluorine. You can see this example right here. A single fluorine atom can perturb the pKa about 1 unit there. we lose a little bit of potency, but the bioavailability shoots up. Can get through membranes better. Remember, protonation states, they're ratios, right? These are logarithmic ratios of being protonated versus non-protonated. So if you have enough of the compound neutral under physiological conditions in a reversible equilibrium, then it can still get through. The neutral part can get through, the cationic part might not. But it's an equilibrium. That proton's going on, off, on, off, on, off. So we get a good bioavailability here. For engagement of the receptor, and for many CNS drugs this is true, for engaging the receptor, many times you need a cationic amine. You need that amine to be protonated. So you need a little bit of basicity in the molecule. So if you put a second fluorine atom on the molecule, you lose potency pretty significantly. So you can push it too far the wrong way if you put too much fluorine on it. Okay, but look at the change in pKa. We have 3 log units relative to the parent compound there. Okay, so if you needed that thing to be always or as much as possible neutral, that still might be a good substitution. You just can't do that with a lot of CNS therapeutics. And you can perturb that basicity even more with other heteroatoms. So the signal withdrawing effect, oxygen is pretty electronegative too. So you can see that type of a perturbation of the pKa. Just for teaching purposes, you can regain some potency because the receptor still accepts a hydrogen bond accepting group at this position. So we regain some potency, but still not as good, still not in the 300 picomolar range, but I think it's a good instructive lesson for how powerful modulation of pKa of amines can be using fluorine. So this is the last example before our break. So this is an FDA-approved therapeutic. Yep.
Yeah, sorry, I had one.
On this one? Yep.
This was again very interesting example. I was just trying to correlate the activity change with not only the electronegativity but also the conformational things what we were discussing in the last class. Like because of the fluorine, is it also possible that it is changing the conformation such that maybe the activity also can be lost because of the that specific conformation which is difficult to fit into the problem?
Yeah, sure. There could be conformational consequences of fluorination that they're not discussing. This is a 99 paper, so maybe a modern analysis or reanalysis would have a different an additional interpretation. Certainly think about the conformations would be relevant. Perhaps it'd be really interesting to make the 2 enantiomers fluoro, R versus S, and get a feel for maybe one of them super, super, super potent, and the other one is like not as good. Maybe there'd be something good. I don't know about the value of 5-HT1D right now, and if people are really excited about 5-HT1D. So there's also a should you do it. These serotonergic agents could be kind of tricky, and a lot of other things can happen when you're messing with serotonergic receptors. I don't know the recent history of 1D and how good of a target it is. So this is Januvia. This is an FDA-approved therapeutic. This is a fluorinated drug. The accepted drug is right here. It has the CF3 group. And this is a study in which we will look at a series of compounds in which we change the substituent R1 right there. Okay? So in terms of inhibitory potency, you can see the series of values here. For the series, the hydrogen is a little bit less potent. You get a slight improvement in potency as you put in the ethyl group, a little bit of grease there, a little bit more potent with the CF3. If you get too big in that space, you lose a little bit of the potency, but 71 nanomolar is still pretty good, right? So not big change there. As you fluorinate this molecule, there's a little bit of change in the clearance, the metabolism, but it's not substantial. It's not a big driver here. These clearance rates and the half-life are reasonably close to each other. The big changes you get here are in the distribution. So Cmax, that's the maximum concentration of the drug through an oral dose. In this case, if you dose this drug orally with the H or the ethyl, none of that gets in the body. That thing does not get into systemic circulation. And when you put fluorinated groups at the position right here, the 2 position of the heterocycle, now we start to see substantial concentrations of the drug in the body. Oral bioavailability, this is F, this is the percentage of the drug that enters into systemic circulation with an oral dose. That goes from single digit up to 70% with that fluorinated substitution. And the rationalization here is that we're perturbing the basicity of these such that they dehydrate well as the molecule is approaching the membranes. Okay. So that's the rationalization there in terms of pKa's. This is one that I'd like to do and send somebody off to go say, you go do the calculation and convince yourself that there's a change in the basicity of these positions. And you would want to be protonating this and making the amine, protonating this and making the heterocyclic protonated form. And I think this is a good exercise, again, for somebody to go do and calculate the pKa's of those and convince yourself that there's an important change there to track. So we do have a couple of other examples in the afternoon that are going to have a similar heterocycle where we do have some data to look at there. So I'm covering that scientifically. I'm comfortable because of what we're going to see later. Okay. So are we close enough to on time? We can pause for a little bit now. It's a good time for a tea break for everybody, and then I can reset myself mentally for the second half. And we'll have a good, thoughtful discussion in just a little bit, all right? Cool.
Yeah, I just wanted to make a note here. So I think Professor Atman has given the wonderful examples. So just if you just think about now any other example, like suppose instead of fluorine, in your molecules, if you have fluorine, methoxy, or cyano, any other groups, then the concept will remain same because the inductive effect, the conformational effects, and its change on the pKa, pKb, or the other IC50 values of you see. So definitely, I think this will be definitely useful, even though if you are not into fluorine chemistry also. These concepts as a medicinal chemist, they are really amazing. So those who actually will work eventually in the pharmaceutical R&D labs, you will see that now R&D works they not only try to improve the activity of the molecules, IC50 or EC50, but they also want to improve the PK properties of the molecule. So that's why I think these discussions will become very useful. Okay, so I think with this note, let's break for a tea.
What time do we come back?
Yeah, 15 minutes, 15, 20 minutes. 11:10. 11:10, 20 minutes break.
11:05?
No, it's 50, right? No?
Yeah, 50. 15
Yeah,
minutes
so
would be
so
11:05.
11:10. So I'm assuming 10:50. So 10 minutes and then 11:10 we.
Okay.
We have some.
I'm doing like this to show you my watch instead of just telling you. Oh, I gotta sit.
Yeah.
How you doing? Good morning. Oh, hi. How you doing? I think we emailed about one of your students went to KU, right? How did? She must be graduating or half graduated. One of your students went to KU right as I was leaving. Did you run a master's student? Okay.
Yeah, actually, I think our advisor moved to Chicago, University of Chicago. I think last year, I think they
From Kansas.
Kansas.
Jingshan.
Yeah, I know. He's
Yeah.
advisor's name.
I didn't know she was this year, but that's fine. I thought Jingshan was awesome, super high trajectory, difficult science, very biological. He was a chemist, but the biology was really driving their discovery. Yeah, I remember that. Quick series of emails.
I think he joined maybe after.
Yeah, he did. We lost a lot of faculty at KU back then. And then he was one of the young appointees. We hired 5 assistant professors in 3 years. It was like massive, quick hiring spree. He was the final, the last one, I think.
Similarly, I asked for professor.
Yeah. Pleasure to meet you, Jay.
Yeah, so I mean, then, so when you moved to Purdue?
2020. And so this is why I remember it. It it was very clear because there were some students that were, every year there's a few students emailing you more than others. She was one of them. And then you remember your letter. I knew that I was leaving the university, and even though like you signed the documents, you're negotiating with the other university. I know I'm probably going to go, and so you know in that interaction, I was very much trying to not focus on my group, but you know the benefits of KU, or you know talk more generally about the different options and lots of research, lots of rotations, but not trying to like I'm going to leave. I should take these students, right? I didn't want to take you know good students from my colleagues. So that was that. Yeah, it was 2020.
Yeah, and similar kind of things happened with another faculty who also moved to Purdue. I think maybe 2 years ago, being you.
Oh yeah, yeah. Do you know me?
Yeah.
Okay, awesome.
So
Yeah, he's a good colleague.
yeah. So one of my students actually wanted to do PhD with him when he was in Stony Brook, and then last time he left, he was about to leave, and then he said, "No, I cannot take you. Let me join another group."
Yep. Okay, but he's okay over there now.
What
group?
He,
Ojima is still taking students, or no?
I think Jeff, I think, initially joined,
Okay.
but then he later changed. Now he is now the medicinal chemist for some Japanese.
Ojima.
Ojima, yes.
Wow, Ojima is a legend, right?
Yes, yes. He moved to his group now. Yeah.
Yep.
Initially joined a different group, but then I think he had some difficulties.
Right.
Yeah. So.
Ojima is somebody I feel like he would have retired 10 years ago. He's still going.
Yes.
We started at 9:40
Yeah.
or so.
9:40, that's just 10 years.
Or I mean, I know some other people like my more than 2, 3 actually PhDs, those who are pursuing postdoc and have pursued postdoc in Purdue. That's why I know Harlan very well. Harlan Sethi and then Gaurav Chopra.
Right. Okay. Yeah.
Yeah.
Arun goes. Yeah. Arun.
Arun, I have never met him, but then yeah, I know by name.
Yeah. Who else? The other one that some people seem to know a lot is Ramachandran.
Yes,
He's
Ramachandran.
Ramachandran.
Yeah, the name I met him.
Yeah.
But then, yeah, we were like, like initially, I think Harvard also moved from Purdue to
Notre Dame.
Notre Dame, yes.
Yeah, I think that was maybe 6 months ago.
Mm.
It was over the summer.
Yeah. Still one of my like former PhD students working with him postdoc. He joined Purdue, but
Yep. Yeah, Herman was weird.
he moved from Baltimore, I think, somewhere, right?
Yeah, he's in Maryland.
Maryland, yes.
And your student that went to Chicago, went to KU and then moved to Chicago.
It's Shalaka.
Yeah. So
Look,
antibiotics like cyclic peptides, which are there,
Mhm.
right? So they have to somehow, and cyclic peptides are also good for integral membrane protein like things across the thing. So then,
Sure. But-
having fluorination mutation in one such phenylalanine, whether that might also have a very profound effect in that way.
Yeah, I mean, there's some antibiotics by which you can change the distribution properties into bacteria using fluorine. And so the fluoroquinolones would be one example. So the early generation fluoroquinolones were not fluoroquinolones, they're quinolones. Very limited spectrum, limited distribution. And when they put the fluorine atom there, they improved the distribution across mammalian physiological membranes, but also in bacteria. You got an increase in distribution into the bugs. There's some other derivatives too. In the case of peptide-based antimicrobials, you have to be kind of cautious because many of those engage the membrane, and their target is on the membrane or outside the membrane, and some others might enter through porins. In gram-negatives, you can get through porins. So there are multiple modes of entry into bacteria. So what's going on with antibacterials is really tricky in terms of are they getting into the cell or not. Yeah, we got that. Oh, we came back over here. That bug's back over here. Okay. So anyway, we can get back and moving back into material, and these are going to be a lot of case studies here. Not necessarily the tutorial that we did before, but case studies instead. And so many of the molecules we look at are going to be CNS therapeutics in this series. And for CNS therapeutics, you need a molecule to engage a target in the brain. It's a tough organ, it's a tough compartment to get a molecule into because of the structure. And this barrier we call the blood-brain barrier. So you can see the brain, you can see capillaries distributing all around. Here's another view of that, and the blood-brain barrier is an endothelial layer of cells that lines the capillary, and it's going to have certain proteins that resist drug entry or xenobiotic entry. Okay? So in order for a drug going through systemic circulation to get into the brain and reach a CNS target, you're going to need to get past this barrier. And what's going on at this barrier? Well, you're going to need a molecule, or how do you get a molecule past this barrier? You need a molecule that's sufficiently lipophilic that they can get across physiological membranes. The junctions of these cells are really tight, and it's tough for molecules to squeeze between the cells here. And that's important when you think about it, because you want the blood-brain barrier to reject a lot of things that shouldn't be in the brain. You don't want neurotoxicity from random things that you're getting you're exposed to. So the junctions are tight here. The molecule would need to get through the membrane since you need the right balance of log P, but it also needs to avoid rejection from proteins whose main role is to identify molecules that should not be in the brain and reject them. There are various different forms. PGP is a common one. P-glycoprotein, PGP. Breast cancer resistant protein is another one that you'll see quite a bit in literature. There are other transporters that can help facilitate entry of drugs. This would be an anionic, organic anion transport protein. And so there's a range of transport proteins that recognize cargo, bring them in, push them out, and really regulate what gets into the brain. And we're particularly concerned in this case about PGP, BCRP, but PGP is a big one you see when we're thinking about the blood-brain barrier. Okay, so we're going to be talking about that. You'll be using the term PGP. Your slide looks like this. Just kind of summarize those two figures on one slide. Okay, so as we go through this material, we should be asking about the types of molecules that are likely going to get into the brain. How do we rationally design drugs that should get into the brain for neurotherapeutic? And then on top of that, how does fluorine modulate properties related to these two questions? Okay, so you first have to understand what types of molecules get into the brain first, then we can think about how does fluorine modulate those properties. So let's go ahead and think about molecules and quantifying metrics that describe molecules. I already did the quick survey at the beginning of people who know Lipinski, one of the most well-known series of metrics that predict whether a molecule might be a good drug, a valuable drug. Lipinski's rules you don't want to overinterpret them. They're only estimating whether a molecule is likely to be orally bioavailable, not whether the molecule is going to be a drug overall. Okay, Lipinski, when he originally wrote those rules, is just looking at, is it likely to be orally bioavailable? That's it. Okay. Well, that's for a molecule going through the barrier of the GI tract and avoiding some of the first-pass metabolism that occurs in the liver. That's not necessarily the same type of molecule that's going to get into the brain. So there might be different rules, different quantifiable metrics that can be identified for molecules that are going to get into the brain. And this is one algorithm. This is one scoring system that Pfizer developed maybe a decade ago. CNS MPO, multi-parameter optimization. You can see that in the red on the side. Okay. So this is kind of like Lipinski's rules for the brain. Okay. And so we need a balance of lipophilicity. We need either log P and log D to be within a desirable range. We don't want molecules to be too greasy, but we also need them sufficiently greasy so that they can get across the membranes and also avoid PGP. And I'll explain the difference in those in a little bit. But you need a balance of log P, there's a certain range you want, and log D, and there's a certain range you want to be in here. Lipinski, they have that cutoff of molecular weight 500, and for CNS molecules, you typically want them to be even smaller. So some estimates say less than 400. In this case, preferable or desirable molecular weight would be less than 360. So we want a little bit smaller molecule. We definitely don't want it to be big, over 500. Not many neurotherapeutics get in that range. But you can get things, in the 400 range that are still pretty good, okay? Polar surface area is really important. Polar surface area typically correlates with the number of nitrogen and oxygens in your molecule. Those are the main drivers for polar surface area. You don't want that molecule to be too polar, and you can see the threshold there, usually about 120. And these are square angstroms is the unit that we're looking at here. And sorry, you don't want to be over 90. But you definitely don't want to be over 120. You also don't want it to be too greasy. Okay, and we already talked a little bit about grease. If you're too greasy, 3 problems. I identified them in the first part of the talk. It can sit in the membrane and just stay in the membrane. Metabolism can be an issue. What else? Poor solubility overall. If you're too lipophilic, you just might not be soluble at all. So a couple of different concerns if you're too greasy. Polar surface area is also looking at grease-like nature, grease-like character. Number of hydrogen bond donors. Really important. We were talking about hydrogen bond donors and how fluorine can perturb the hydrogen bond donating or accepting capabilities of the nitrogen and oxygen heteroatom. So fluorine can definitely perturb that property there. We don't want too many hydrogen bond donors, and I'll explain why in just a little bit. And then the acidity of the molecule. When we have basic amines, we don't want them to be fully protonated. We need them to be, if they're too basic and they're fully cationic, they'll struggle to get across the blood-brain barrier. So we need to tamper down the basicity, make it such that they can be neutral in the equilibrium, protonation, deprotonation, it's in equilibrium. We need them to be sufficiently acidic that they can give up that proton, get to a neutral state, and then they can get across the blood-brain barrier. So this is kind of like Lipinski's rules just for the CNS. There are various different quantitative metrics. This is one scoring system. Different companies have different criteria, and so you can look up newer versions or other versions of these. And then and you can compare and contrast them, but I'm just kind of teaching one as a prototypical example right now. So this model overall accounts for 2 general properties. Passive diffusion. Is the molecule going to get into the brain, number 1? And number 2, is it going to avoid efflux by PGP? So there are 2 things there. Now we know the types of molecules that will enter by passive diffusion. We need them just to be greasy enough and water soluble enough. If we're just going across a membrane alone, that's all we have to think about, really. The problem is when you think about PGP, now there's a different challenge, and what types of molecules does PGP recognize should come to the forefront of your thinking? The problem here is that we have two different properties that are estimated by one set of parameters, so we now need to disconnect those two properties and come up with another model and just ask the question, well, what avoids PGP? And so there are different metrics or scoring systems, trends, that do decouple PGP from distribution. PGP is P-glycoprotein. That's one of the, that's like this right here, one of those proteins that effluxes molecules, stops them from getting into the brain.
So it prevents.
It prevents molecules from getting into the brain. So we want to avoid efflux by PGP. So PGP is a liability and something we want to avoid. So what types of molecules will avoid PGP? Yep. Okay. So PGP is found, yes, in the brain, but it's also found in different different organs. So it's a big challenge avoiding PGP for many reasons, but right now we're just thinking about entry into the brain and rejection of molecules from the brain into the blood. So there are, again, several different metrics or scoring algorithms for predicting whether a molecule will be rejected by PGP or not. This is one of them that I like. In this assessment of PGP risk, you can get increased PGP risk. If you have high nitrogen oxygen content, you want number of nitrogen and oxygen to be less than 8. You get over 8, high PGP risk. Molecular weight over 400, not good. And you don't want acids that are too acidic. If they're too anionic, that as a trend increases PGP risk. And by say PGP risk, that's likely going to be a substrate for PGP. If it's a substrate for PGP, it doesn't get into the brain. So that's how you increase PGP risk. To decrease PGP risk, the opposite is true. You want to keep your heteroatoms, your nitrogen and oxygen heteroatoms low. 4 or less is good, molecular weight less than 400. But you also want to think about the amines in your molecule and make sure they're not fully cationic. You need them to deprotonate and get to a neutral state to avoid PGP. Okay, so there are a couple of different trends here. Some of them are related to the ones we saw before. There's no log P, there's no lipophilicity. I'll point out a couple of things that are similar between these two. The molecular weight, roughly the same. One of them says 360, one says 400. Okay, yeah, that's pretty close. The heteroatom count is really
increased PGP risk means the
likely effluxed.
Okay, so then
Likely efflux does not get into the brain. If you increase and this is terminology that's used by medicinal chemists. Yep. It's a terminology that's common. You just you adjust to it.
You increase PGP risk means it is actually better. No, it is not better, right?
Likely to be effluxed.
Likely to be efflux. So that means
Which does not get into the brain.
Not going to the brain.
Yep.
So
I try to make it red bad.
Okay.
In terms of my labeling, red is bad here.
Okay.
Yep.
So for our drug, that we do not want to increase the PGP risk.
If you're trying to make a CNS therapeutic, don't and that lesson is down here. Don't have too many nitrogen and oxygen, hydrogen bond donors, acceptors. Don't make it too big, and don't make it too acidic. At the same time, and this is kind of like the two sides of the same coin, make sure you have fewer hydrogen bond donors and acceptors. This count about 4 or less. You want to be smaller molecules, but you also have to think about the basicity of the amine, and you don't want it fully protonated. Okay, so the key lessons are down here in this slide, or how you should interpret it, how you should think about the design concepts. But we can also compare these rules to the other ones, CNS MPO, and see that they track a little bit. So when we think about the number of heteroatoms I suggested before are going to also correlate with the polar surface area. So they're not the same metric, but they track with each other. As we add more and more and more nitrogen and oxygen, our polar surface area is going to increase. And if we have more and more and more hydrogen bond donors, You're also going to see your nitrogen or oxygen increase as you add those donors in, okay? So they partially correlate even though they're not tracking the exact same thing. And then the pKa of the basic amine is also important for most metrics, and I also said the size. Again, the main difference is the PGP rules don't seem to track log P very much. That's the main difference, okay? Oops, let me go forward instead of back. Okay, so does this make sense to everybody? Automatically. Who has studied cellular assays to predict distribution of compounds across membranes? Have you seen CACO2, MDCK, PAMPA? Okay, I see a lot of no's. I see a couple yeses, but I see quite a few no's. So we're going to go through this, and I wasn't sure, and thank you for, very visually. Sometimes you teach a class and people are just like, they just look at you, and you ask a question and they're just looking at you, and I don't know the answer, like you have to tell me something, so it helps me adjust to the audience here. So there are a few assays that are conducted regularly in industrial settings, and academic labs can also either run these assays. They're actually pretty tough to run these in academic labs because you have to grow the cellular assays a certain way, the cell layers a certain way. But there are contract research companies that you can send your compounds to, and they can run these pretty easily too. And so in these assays, they're built around a technology in which we will make a membrane and have two different compartments, a compartment above the membrane and a compartment below the membrane. This can be a cellular layer, or it can just be like an artificial membrane. So initially, we're going to talk about a cellular membrane, and that's what's drawn up here. Now, this cellular membrane can be made of a couple of different cell types are common. You have CACO2s and MDCKs. You can see where those cell lines originate from down here. CACO2s are better for predicting oral absorption. Some people use it to correlate with CNS, compounds getting into the CNS. MDCKs, many people think are better for CNS distribution, and there are various different modified versions of the MDCK cell line that you'll also see in the literature, RRCK or MDCK low expression. This is a canine kidney dog cell in which they express PGP to use as a model for the CNS. Okay, and so that's what's going on here. This cell line has PGP in it. This one doesn't have the same distribution, but this is an intestinal cell line. Again, we use it many times to predict whether a compound's going to go across the GI tract and make into systemic circulation from an oral dose. So in this assay, you would typically run it in two different directions. In one direction, you would place the drug on the top layer, the apical layer, and measure the rate at which the compound diffuses across the membrane. Okay, so you're measuring a rate of drug going across the membrane, and then you take the same cell layer in a new well and you put the drug in the basolateral side and you run it the other way. If there is no efflux, the directions, the rates should be the same. The ratio should be 1. If you have efflux, the ratio going from basolateral this way will be faster than the rate going downward from A to B. And in the reports you see rate A to B and rate B to A. Divide one by the other, you get a ratio, and that ratio estimates whether your drug is getting effluxed. Okay, so two key pieces of data there that we get. We get the rate going each way. We also get a ratio of the two, and the ratio is a lot of the data that you're going to be seeing on the subsequent series of slides. Okay? So that's the technology that we're using here for this assay. Again, you have CACO2s, you have MDCKs. We're going to see data from both of these. PAMPA is another one that's used a little bit less. PAMPA is just like a phospholipid layer. It's not a cell. So it doesn't replicate efflux, but it just answers the question, can my compound make it through by passive diffusion? And you only have to run that unidirectional. You don't have to run that bidirectional because there's no efflux mechanism. Okay. Let's see, there's one other thing. Oh, there's one other thing that is important here. The other data point that you should be looking at is recovery of your compound. So if you're losing compound because there's some metabolism or instability in the molecule, you'll see that because it just quantitatively you won't find all the compound. You also in some cases can see compounds that are too greasy sit in the membrane. and then you lose material that way. And if you have certain types of plastics, the compounds can actually just sit on the side of the tube, and so there are ways to get around that. So you need to make sure the person doing these studies knows all the tricks. If you run this in the presence of some serum or albumin, then you get away from the loss of material on the sides of the wells. Okay. Important assays, you see this data a lot in literature, JMedChem, ACS MedChem Let, any of the other MedChem heavy journals. This is routine, regular. Anybody doing industrial MedChem, you're going to see this data all the time. Okay, so we're going to see data from those assays. Thank you for giving me a couple of minutes to talk about that. Now we're going to systematically walk through examples in which we can track the heteroatom count. And how do we minimize heteroatoms? We know that we can always strip heteroatoms out of molecules, but there are other strategies, other techniques, other tricks that we can use to avoid PGP by patterning our molecules a certain way. So go ahead. Yeah.
So if you want to target CNS target, if we design the drug of the CNS target, right? So you have discussed about some rules, but that
Trends. Okay, so I know people say rules, and I think never take a rule as a rule. These are trends. There are many outliers to the trends, and for any of these rules, you'll find drugs. Yep.
Stick to that trend.
Mm-hmm.
To reach to the CNS, it has to pass from the intestinal barrier as well, right? So we need to correlate
Not if-
the rule and that CNS rule.
Sure.
By design, right?
Yeah. So there's an assumption there that you want an oral drug that has to go through the GI tract and then get to the CNS. You can give an injectable drug that gets into the CNS also. I'm not sure you always want to do that. Most of the CNS active drugs, they're typically orally bioavailable. The trends that you see here are more stringent but compliant predominantly with Lipinski and beyond rule of 5 and some of the other metrics that are used by different companies. And again, Lipinski is old. There are many different newer iterations that have refined the concepts, said, these couple of properties aren't important, but these other ones are, so you have various versions of BRO5, beyond rule of 5 rules. And you can find, if you went online, did a quick search, you probably come up with 20 different papers that give some other variant of Lipinski that is still trying to estimate whether a compound's going to be orally bioavailable and avoid metabolism sufficiently. And Lipinski was only looking at oral bioavailability. He wasn't looking at all the other things that the metabolism did. Okay. But most of these are within Lipinski parameters. So if you're compliant here, you're likely compliant within Lipinski, and you're likely compliant with some of the other metrics that are out there. More than not. Okay. Not always, but more than not. Okay. So we've learned about our assays that we're going to see, and now we're going to figure out strategies for avoiding PGP efflux. And initially, we're going to look at a really cool, unique strategy for avoiding efflux by masking or hiding hydrogen bond donors and acceptors. So in this strategy, we'll look at a matched pair, and these molecules are basically the same for many practical purposes. You can see the only difference is we rotated the pyridinyl nitrogen from the 4 position of this amino acid derivative over to the 2 position. So you can see it there. Same molecular weight, they're isomers of each other. C log P is effectively the same. Polar surface area, they have the same number of oxygen and nitrogen and everything. That's exactly the same. The pK, there's a slight difference as you bring the nitrogen closer into the ring, but not all that different. The difference in these compounds is the effective hydrogen bond donor and acceptor counts. So there's been recent studies demonstrating that if you engage a hydrogen bond donor in an intramolecular hydrogen bond, it effectively masks that hydrogen bond, the hydrogen bond donor. It masks it from PGP. You're hiding it so PGP doesn't recognize it. And then we minimize PGP risk, lower PGP risk, more likely to get into the CNS. And so that's what's shown down here in the next series of data. You can see the hydrogen bond donor count. Here's a donor, right? that goes effectively down 1 because we've engaged it in an intramolecular hydrogen bond. And you see the PGP risk is minimized. This is the A to B direction. It goes from A to B 6 times faster. That's pretty good, right? And then, 4 times faster. And then our PGP efflux ratio goes from 3 down to 1, and that 1 is like there's no efflux, right? 1.1 is 1 for practical purposes experimentally for this technique, okay? So we can minimize PGP risk through intramolecular hydrogen bonding interactions. Here's another example that shows the same type of thing. In this case, we're going to use a ketone, not always found in too many drugs, but we're going to use a ketone in an intramolecular hydrogen bond to mask this NH here. So these two molecules, we can compare many of the properties of them. Effectively, the same size, 466 versus 462. PGP isn't going to care about that difference. Lipophilicity is reasonably similar. pKa is a little bit different. Polar surface area. This molecule has less polar surface area than this one. Remember sulfur? Not particularly polar, right? Its electrons are very diffuse, and it's not quite as electronegative as oxygen. So it is not necessarily the most polar element. Okay? So when we replace that sulfur with the carbonyl, our polar surface area actually increases, and it's kind of at that threshold that MPO says is starting to be risky. We don't want to go too much beyond that, but we're right at the threshold here. Nonetheless, the effective hydrogen bond donor count has decreased. So we've gone from hydrogen bond donor here, hydrogen bond donor there, effectively 2 hydrogen bond donors down to 1. Here's 1, but this one is masked in an intramolecular hydrogen bond, and it minimizes PGP 8-fold, PGP risk 8-fold.
So when we're talking about PGP efflux ratio and it is getting reduced, that means what is happening? The A to B is going very good, but B to A is not happening.
Right. So
the efflux does not happen.
Yeah, lowering.
Diffusion is happening.
Yep.
But then efflux is not happening, and that's
Yep.
the ratio you are. So basically, the ratio you are taking, that is efflux divided by diffusion. So that's why
Well, it's tricky because diffusion goes both ways. When you put a molecule down here,
yeah.
it will diffuse at the same rate upwards as it will when you put it here and go downwards. So the diffusion goes both ways.
Yeah. But the
efflux
is not there. That is why the overall ratio goes down.
Yep.
And the ratio goes down means it actually goes into the basolateral layer from the AP.
Right. Right. So when you have that, the efflux ratio is estimating, is efflux happening and to what extent? And it's the ratio. Yep. Okay. So even though this molecule has a higher polar surface area, we've taken a sulfur and put in an extra oxygen atom. That oxygen, the nitrogen oxygen count has actually gone upwards. It behaves as a less polar molecule with fewer hydrogen bond donors because there's an intramolecular hydrogen bond there. You're masking that from the PGP. And it's a pretty profound effect there, right? And I mentioned 8-fold change, going the opposite way from what the numbers actually suggest they should go. It's really cool, okay? So this is a pretty powerful effect. It can be used in many ways. I showed a couple examples that have nothing to do with fluorine chemistry. This is a general principle, general concept. I've heard several companies, speakers from several companies that all use this type of strategy. So it's not like this one company trying to sell it, like many people are using this strategy. But you can use fluorinated substituents in intramolecular hydrogen bonds. We said those are real. We saw some examples the last couple of days where we definitely have intramolecular hydrogen bonding interactions with fluorine. We can use fluorine to engage NHs of amides or amines. You can use phenolic hydroxyl groups. You can also cyclize with those and hide, mask an OH group. So we can use fluorine, but we can also use other basic groups, nitriles, pyridines. We saw an example there, because there's a lot of different ways you can exploit this strategy to minimize PGP risk. It's one strategy that you can use. Okay? How are we doing? We good? Cool? All right. Now, the second property that we'll talk about is modulation of pKa. And this is one of the huge points, like for the entire course, modulate amine pKa's. And so we're going to go through a simple series of examples here in which we're going to modulate the pKa of amines, make them less basic so that they can increase entry into the CNS. Okay, so that's the concept that we're going to talk about here. First, we'll look at this one example. And so in this example, we're looking at a series of aliphatic amines. So the pKa's of primary, secondary aliphatic amines are in that range of 9 to 10 roughly. So just one of those numbers you just keep in your head as a medicinal chemist. I have an aliphatic basic amine, 9 to 10, sometimes depending on what it is, might be 8 to 10 range. Just plant that in your head and don't forget it as a medicinal chemist, ever, until you retire. And then if you're a consultant, you need to remember it still then. Okay, so the series of compounds that we're going to look at is going to be like a primary amine, and then you have an ethylamine, and then a series of fluoroalkyl ethylamines. In this case, the fluorination, I'm going to wait for that plane to fly, because I can't hear myself over it, so that's bad. Okay, so the nitrogen will be connected over here, so the fluorine is a couple of atoms away, right? You have a CH2 and then the fluoromethyl group here. In this series, fluorination definitely modulates the basicity, and we know that. We studied that in the first half, so I don't need to re-explain it, but you can see the magnitude of change here. It's almost 5 pK units as we go from here to there, over 5 pK units here, 5.5 as you go from ethylamine down to trifluoroethylamine. So pretty powerful effect. You definitely see a huge change in the efflux ratio. Okay? Wow. Like, I never see people publish numbers that high. It's nice to see that number because sometimes they just don't even report that compound. It's a really nice compound to see for purposes of teaching.
So the MDR ratio is that same efflux ratio here? I mean, what is that?
Yeah, so this is efflux ratio. And so
Maybe the experiment is?
multi-drug resistance protein.
Okay.
So there are several different efflux pumps, and MDR is just a different efflux pump. Yep.
So basically here, if you increase the fluorination on the side, so then that actually drastically reduces the
efflux. So you decrease efflux. So we're talking about let's go back one slide here. We're talking about, there. So we're talking about modulating the basicity of the amine. And you don't want it to be locked in a fully cationic form. And if you can tamper it down so that your pKa is less than 8, you got a better chance. Yep. And so, but you get really good. Like 3 is okay. I'd love to have it 2 or below, ideally. And so if you tamper it all the way down to 5, that ratio is perfect. Like you can't get better than 1 in this assay by definition. But even if you got it to 7, you're still like in that ballpark where maybe a fine tune somewhere else on the drug gets you there. Okay. But anyway, you can see the correlation between pKa of the amine, the basicity of the amine. Again, that basicity correlates with how much of it is cationic under physiological conditions. You can see that correlation pretty well with the efflux ratio. Okay. Lipophilicity also tracks as you would expect. As you add fluorine into the molecule, you get a little bit greasier, a little bit greasier, a little bit greasier. In this case, pushing the limit, 3.4, 3, that's kind of getting the threshold. You start thinking, we don't want to go too much greasier, likely, unless we have the assays to say we're okay for stability. But just recognize as you keep making things greasier and greasier and greasier, you might have other problems. And so everything's like Goldilocks. Too much bad, too little bad. You're always looking for just the right little amount there. Okay, Aristotle's golden mean might be another way to think about it. Here's another example. It looks similar to Januvia. When we look at this heterocycle over here, it looks a lot like the one I said, go try it for yourself, go do some calculations on your own. Nonetheless, it is another example in which we're going to substitute the the 2 position with the heterocycle with a variety of different alkyl groups or fluoroalkyl groups and evaluate how that affects the efflux ratio. In this model, we're using those CACO2 cells. So instead of just a CNS therapeutic, we're looking at oral absorption data here, or estimate of oral absorption. Some people do use CACO2s to predict CNS permeation. Okay, I think MDCK, if you tracks a little bit better. It's not perfect. Neither one is perfect. They're both models. Okay, but CACO2s are used sometimes also. Okay, so let's start digging through the data. As we increase fluorine, this would be your isopropyl, monofluoroisopropyl, in which that fluoro group is between the 2 methyl groups. That data is shown here. You see that decrease in efflux, and that's great. If we have a CF2CH3, so that'd be a difluoroethyl group, efflux is even better. Okay, so we can just tinker with fluorine to that position, put too much in there, it goes the wrong way. Many of these compounds are reasonably potent. So 50 nanomolar is pretty good, 40 nanomolar is pretty good. You get things that are a little bit too greasy, too bulky in that space, that you lose potency. So again, as you adjust one property and kind of tune that, if you go too far, we lose potency. So you got to watch out for that. Always track all your parameters. That correlates with the basicity of these 2 positions. And so as we add fluorine, we become less and less and less basic. You can see that in the data. You can see the correlation between the efflux, inverse correlation, the efflux and the basicity there. Okay. Percent oral bioavailability is generally good if you can tamper down the efflux. Here we have a lot of efflux. Oral bioavailability is reasonably poor. If we can tamper down the efflux a bit, then we can get an orally bioavailable compound that we can measure sufficient concentrations in vivo. Okay. Oh. Uh-oh. This is working. That's working. Is the camera still working? Okay, awesome. Okay. So we can still keep going here. But anyway, this is, again, another slide that does show that many times these cell lines, these monolayer cell line assays, can estimate oral bioavailability reasonably well. Okay, so that was the series of slides there looking at the basicity of the amines there, and now we can start thinking about molecular weight. And so this is an important one to think about, because when we think about this property or this strategy of adding fluorine and more fluorine and more fluorine, well, if we keep adding fluorine, aren't we going to increase molecular weight? Fluorine has a mass of 19. So each fluorine atom we add is roughly, it's 18 units. Because you have to remove 1 hydrogen to put on a fluorine, right? So it's a change of 18 in the net change. So if you keep adding more and more and more fluorine, and we're already near the ceiling of 400, are we gonna, you put a CF3 on and we've jumped up, 54 units? That might not be good. And you see some of the FDA-approved therapeutics now that'll have 2 CF3 groups, or 2 CF3 groups and 3 other individual fluorine atoms on it. Wow, like that could give you this huge molecular weight jump that could be problematic. Okay, and that's been studied, and it turns out that the addition of fluorine atoms does not contribute to an increase in PGP risk. Even though you're adding molecular weight by the addition of fluorine atoms, it does not increase PGP risk. So it leads to this concept called fluorine-adjusted molecular weight. That concept is about a decade old now. And in this concept, when we're thinking about PGP risk, you consider the molecular weight of the compound in the absence of the fluorine atom. So I take the whole molecular weight, subtract out all the fluorine atoms, use that as the effective molecular weight. So this is a study done by Pfizer, the Pedersen group there. And so let me just calibrate everybody what's going on in this plot. You have molecular weight over on the x-axis here, and you have PGP efflux risk on the bottom. And the numbers mean, this is a study of 150,000 compounds nearly. A number of 0.5 means like you have a 50-50 chance of being being effluxed or not. 0.75, we have a 3-to-1 risk, sorry, a 3-to-1 chance of getting into the CNS and avoiding efflux. Okay, so that's what these numbers mean. It's a probability of being effluxed.
What is that N you said, 149%?
The number of compounds in their library that were used to establish this data. So this is statistical data. 150,000 compounds from Pfizer's library that they had PGP, MDR risk for, and they could use to look for trends. Okay. So what we learned from this data, and I'll walk through it in a bit, what we learned from this data is that fluorinated compounds behave effectively smaller than their molecular weight. Okay. So let's consider, for example, a compound that would be molecular weight 400 with a CF3 group. If we think about molecular weight 400, that's here. Okay. Now the trend lines, this is experimental data, the trend lines for a compound with, let's say, let's use this, 0 fluorine atoms. So if we had a compound that had no fluorine atoms, we would expect 50% risk of efflux. Instead, this compound has 3 fluorine atoms. So that's the cyan color right here, this turquoise-ish color. And look at it right there. It has about a 30% chance of being an efflux substrate. So it's behaving as if it's a smaller compound effectively. Okay. Let's look at maybe another example just for comparison. This is a compound with molecular weight 500, and it has 5 fluorine atoms in it. Okay. If we have a normal compound, molecular weight 500, that's the red trend line that we saw up here, molecular weight 500 with no fluorine atoms is a 75% chance of getting effluxed based on their statistical data from their library of 150,000 compounds. It's a pretty good set of data. In contrast, with 5 fluorine atoms, it behaves as a smaller type of molecule. 5 fluorine atoms and molecular weight 500 is about a 50% PGP risk, not 75%. Okay? So that's what's going on. That's how you would use a chart like this. Okay, but the main point is that as you increase and increase and increase molecular weight with fluorine, you do not increase PGP risk. That goes outside of the original rules that we saw. They just said worry about the molecular weight. Okay, there's a nuance when you're using fluorine to adjust the properties of molecules. Okay. So, for the next series of examples, we're going to look at that concept, but we also need to build in a few other types of data that we're going to look at. And these are really important concepts for modern medicinal chemistry, metric-guided drug discovery. So we're going to briefly introduce ligand efficiency, lipid efficiency, and lipmedi, that's metabolic lipid efficiency. And basically what these parameters estimate is the efficiency of your molecule. How good of a molecule do you have? Okay, so the first parameter is going to look at the energy of binding divided by the number of heavy atoms, carbon, nitrogen, sulfur, fluorine, anything, any heavy atom, non-hydrogen atom basically. Okay. As you add mass to the molecule, you would expect to get more potent and more potent and more potent. But we have to stop and say, okay, for each atom we add, for each moiety we add, are we getting value for the amount of mass we're adding? So this is a factor saying, okay, if we add a phenyl ring, 6 carbon atoms, are we getting a huge jump in binding energy? Or is it kind of like we added a lot of mass, but we didn't get a very big increase in energy? This is just one metric for estimating how efficient is each molecule, the binding energy, how efficient is the addition of new heavy atoms into our molecule. So you want this to have a good number, 0.4 is generally good. how strong are the new interactions or that you're adding, or how important were the interactions that you might be removing, stripping out, okay? Now, this is just looking at binding of a molecule to a target. It doesn't consider all the other properties that are important for drug discovery. So, we might think about lipophilic interactions relative to like hydrogen bond donating accepting interactions, and enthalpic versus entropic interactions. And so the second metric is used for estimating how efficiently you're using your grease or your lipophilic interactions, your enthalpic, entropic interactions. If you add grease to a molecule, maybe you're adding potency, but you might also be adding a metabolic liability. The metabolizing enzymes chew up greasy moieties in the liver predominantly. So we have to ask the question, as we add grease, are we getting a huge jump in potency or just minor jumps in potency? That's what this next metric is looking at. It's a relationship between the potency of the molecule and the lipophilicity. The potency of the molecule needs to be corrected. So you have the P function there, logarithmic correction there. So we can take IC50 values and compare them to the grease. So for each addition of a greasy moiety, we're going to add some log P, some lipophilicity. Are we seeing a substantial logarithmic change in potency of binding? Okay, so that's an important factor. The other one that's not used quite as much is this lip-med-E factor. Some companies love it. Others don't pay as much attention to it. They use their own rules and parameters. But it's a concept called, that just be aware of it and think about what it means, and if you want to use it in your own campaign. Lip-met-E, this is lipophilic metabolism efficiency. So as you add grease, is that grease getting metabolized, or is it grease that's like stable enough and not getting extensively metabolized? So lip-met-E, you take log D and then you subtract the microsomal clearance. Convert that over, logarithmic function there to convert that over to a useful number. And again, it's asking the question, is grease that you add to the molecule extensively metabolized, or is it grease that's not metabolized as much? Okay. So those are three parameters that we're going to be looking at in a series of examples moving forward. Again, there's a quantitative goal here of roughly 2. Quantitative goal about 5 there for lead molecules or late stage molecules. Okay. So here's a series of examples here. And BACE inhibitors, so this was a hot target for Alzheimer's disease some time ago. There were quite a few BACE inhibitors going to clinical trials. They all failed. The A-beta hypothesis doesn't work for Alzheimer's in humans. It works well in mice, but there's got to be something else going on in Alzheimer's. And there are other good explanations for Alzheimer's that people are following up on. So in this matched pair, you have a methyl versus a fluoromethyl group here at this position. For practical purposes, that adds molecular weight 18 to this number, and we're kind of right at the threshold of 400. If we consider the fluorine-adjusted molecular weight, you actually have a little bit, barely, right? But we have a smaller molecule there. Okay. The efflux ratio decreases as we go from here to there. When we look at other parameters, you see some slight changes to the lipophilicity. So this guy's a little bit more lipophilic. You're probably perturbing the basicity of that moiety there. The lipid efficiency is about the same. The potency is about the same. The lipophilicity is about the same. Our lip-E value, therefore, is about the same. Clearance, for all practical purposes, is the same. You do see one other property improve, and that's the Hurg risk. So the Hurg channel is an ion channel in the heart that's important for repolarization. Every single beat of the heart. The cardiomyocytes, as they constrict and repolarize, you need to, that's what this channel is doing. Okay. If you have high affinity to Hurg, that's a major risk, cardiotoxicity risk. You want to avoid that. Hurg recognizes basic amines really well. Greasy amines and basic amines. That's what hERG is great at recognizing. So if we can tune down the basicity of basic moieties, we can reduce PGP risk. So that's what's going on here, and why I include this data here. It's just to remind people that modulating the basicity can have other beneficial properties. Here you want hERG to be higher. We don't want to target hERG. So that's a good step in the right direction here. Okay? So that's the first molecule. And the second molecule, the match pair that we'll look at here, you see a little bit more pronounced effect in fluorine patterning of the molecule. And there are several changes here, so this isn't a perfect matched molecular pair. You have a couple of different changes going on. In one change, you have the T-butyl group replaced with a trifluoromethyl ethyl, or a trifluoroisopropyl group there. You have the fluorine replacing a hydrogen atom over here at the para position of the aryl ether. Now, this one seems to be missing a methyl, but realize that they've actually just placed a new methyl over here. Okay, so you remove a methyl, you place a methyl. They have the same number of methyl groups, okay? Yeah, there's no trick there. Now, this change does increase the potency of the molecule. You can see you go from 100 nanomolar down to a single-digit nanomolar, so we're definitely more potent with these substitutions. That's a great change. In terms of molecular weight, you go from 400 up to nearly 500. So you're right at that threshold where, like, if you had no fluorine in there, there'd be a huge risk, right, of PGP. But using the concept of fluorine-adjusted molecular weight, maybe this molecule behaves a little bit smaller. And you see that in the efflux ratio, right? This is 1.4, a great number. It really doesn't look like what we would expect from a molecule of a molecular weight 500, okay? We've increased the weight without increasing PGP risk using fluorination. Let's think about some of the other parameters for the molecule. The molecule has become more potent, as I mentioned before. The lipophilicity isn't all that different. 3.1, 3.3, pretty darn close. But because we've used our grease more effectively in this molecule, our lip met E value jumps. That quantitative metric saying, as we put lipophilicity in the molecule, is it effectively driving binding of our ligand to our target? That number jumps up. Goal? Yeah, about 5. That's pretty good here. Let's continue to think about the metabolism of the molecule. We'll talk a lot about metabolism tomorrow. For metabolism, we typically use human liver microsomes as a model. Liver microsomes, you take liver tissue, hepatocytes, you grind up the cells, spin them down, and strip out the endoplasmic reticulum so that you can use the enzymes in the ER as a model for the metabolism that's going on in those hepatocytes. That's what HLM is, liver microsomes, and H refers to human as opposed to rat or mouse, which are also used for some studies. So clearance of 100 mils per min per kg is pretty high. We can improve clearance tenfold by getting fluorine in the right substitution patterns. That is evidence, so you can further see that trend by looking at the lip met E parameter. Lip met E going from 0.7 to 2 is favorable. There's grease in the molecule, but it's not getting metabolized quite as extensively as this one is over here. Okay? So that's how we're using a lot of these metrics for guiding the design of compounds, certainly looking at fluorination and how fluorinated substructures can be positioned in molecules to improve potency without increasing PGP risk. We can use our lipids efficiently to drive binding, and they can help avoid metabolism. We're going to talk about the metabolism tomorrow. Okay. I'm going to pause for a second, see how we're doing with questions or other thoughts at this point. I think learning how to, yeah, please.
All these parameters could also be related to the bacterial influx, like designing antibacterials. Bacteria also.
Yeah, so which parameters are you talking about for antibacterials? Are you saying, are these parameters good for antibacterials? Yeah. So these parameters, so they can be, but there's a slightly different challenge, okay? So we can use ligand efficiency for evaluating whether a compound engages a bacterial target, but you'd need a an enzymatic assay to do that, a biochemical-based assay. Okay. The challenge with antibacterials is a lot of compounds don't get in. You have the resistance issue, but you also have permeation issues, right? And so this parameter doesn't deal with permeation. This just says if I have my target and my molecule and they're in some type of a media together, is there good engagement? Okay. So for antibacterial discovery, yes, that's important, but there's a different important parameter. Does the compound get in the bacterial cell well properly? Okay. And with that question, you really want to be using different assays. Okay, so there are different rules for what gets into bacteria, different trends. I don't like rules is kind of harsh, but different trends. A couple of years ago, there was a
Like I think generally the log P is above 3 for bacteria. Like,
yeah. So gram-positive and gram-negative rules are different.
yes.
Gram-negatives want more water-soluble compounds. You can get them through porins. You need rod shapes. You need basic primary amines dangling off of them. So there are certain trends that were identified, and I'd recommend looking at Paul Hergenrother's group at the University of Illinois Urbana-Champaign, who has rules for gram-negative entry. They've been refined, and other groups have developed comparable rules that agree with some of the parameters, make revisions to some of the parameters. So there are a couple of trains of thought. The general trends that I just mentioned are like from one group in the area. With antibacterials, many times you can get away with charged molecules better than you can for like CNS drugs. And so in those cases, the distance or the spacing between the charged moieties matters. The bacterial cells are very anionic, gram-negatives in particular, very anionic on the outer shell, so you have cationic amines, but if they're spaced differently, So there are just different rules, very nuanced. They don't necessarily account, those rules don't really account for this, but they're just different trends and different types of molecules you want to build. Lipid efficiency can be used, but you want to use it intelligently. And so if you're, so it's tricky with bacteria. This one, LipMedi, can be used for everything because that's metabolism. That's the human system. How is it metabolizing the drug? It doesn't have anything to do with the bug, right? So yeah, is that good? Okay, so yeah.
Different therapeutic area. I am talking about anti-cancer, but the answer will be more or less same.
Okay. Yeah, I mean, with cancer, it's really tough because there are different types of cancers, right? Hematological cancers are very different than solid tumors. And there are a lot of genetic differences in cancer. The challenge of getting drugs into solid tumors is really tough, right? Because they have these extra matrices and immune cells that kind of bind and make like a shell outside of some of the cancer. It's a tough problem. I'm not sure of any revised rules for getting compounds into like solid tumors. I just don't know if they're out there. Yep. Okay. Yeah. No, that was you. Yeah.
No, that's very nice. I mean, we learned a lot about how to really, how and how much fluorination we should do in a compound to get that into the CNS targeting. Now, 2-3 quick questions. Maybe, I don't know, maybe you might have talks for that. So, you keep on putting a lot of fluorine in the drugs. So, eventually, the drug has to get
Metabolized?
Yeah, metabolized
and cleared.
Get out from our body. I mean, how easy or difficult that gets when you keep on putting more and more fluorine, because that will also give you toxicity and stuff like that.
Yeah, sure. So the tox is always a question for any drug. Okay. In many drugs, we use fluorine, and we'll talk about some of this tomorrow. You know, if you have things that are metabolized too quickly, it's extremely common to use fluorine to try to perturb the metabolism, block metabolism, disfavor reactive intermediates that form during metabolism. That's very common. When we do that, we do need to check and make sure that the metabolic process does not generate anionic fluoride, because there are some cases in which you put fluorine in a certain site, but it still gets metabolized, and the result is that you push off F minus. That was covered, I think, briefly in Dr. Sulunki's presentation, and it was this paper. It's a great name, The Dark Side of Fluorine. Okay, and I know about that. So I recruited that paper for ACS MedChem Let. So I'm in the acknowledgments of that one actually, and I helped revise and edit that one a little bit. But there are decomposition pathways that can occur that can release F minus, and then fluorosis is bad. You want to be cautious of.
Where do they accumulate or something like
Yeah,
that?
yeah. You want to be cautious of the formation of metabolites that can be toxic. So not the drug itself, but maybe it loses a fluoroacetate, and that can be toxic. That can kill Krebs cycle. So you have to be thoughtful. We're certainly concerned in drug discovery about what happens to the molecule after it's metabolized. You're making reactive intermediates that can cause toxicity, idiosyncratic reactions, allergic reactions. And it's essential for approval to do MET-ID studies, so you make all of the metabolites that actually form. So you make radioactive versions of your drug. Yeah, and then you go identify what those are, you make them, and you study the toxicity of all these metabolites that form.
So another question which is pertaining to this only, because you are focusing on, for some reason, the CNS targeting drugs, right? So you want to get them to the blood across DBB. But then in one or two case studies you showed that it goes there, but I think it has that very high Hodge value, that 10 or something like that, that actually prevents the drug going to the cardiomyocyte, so that it actually causes
It doesn't prevent the drug from going from the cardiomyocyte. It has less affinity for the ion channel that's responsible for the repolarization of the cardiomyocyte.
So that's good. That's an good.
Yeah.
So how do you select? Like you make a new drug, so now you want it to be kind of selective to your CNS targeting, but then there's other organs which are there, like the heart to the liver and all sorts of things. So you will have different metrics for different organs, right?
So more than not, when we're designing a neurotherapeutic, we're hopefully finding targets that don't exist in other organs in the body.
Right.
That's not always true, but that is one strategy. So if we just focus on the selectivity for that receptor,
Right.
and avoid other isoforms of that receptor or other,
but the drug might have also the competition elsewhere. It is possible.
it can get to different parts of the body, and you just need to have amazing pharmacologists or understand the distribution of that compound or that target, and isoforms of that target or different homologous forms of the target. You want to be aware of those if they're in different parts of the body, and if those could cause any undesirable effects. That's certainly something to think about. Like, it's good to think holistically about the entire physiological system and what might be going on. Yeah. You have dopamine receptors here. You have dopamine receptors in your kidneys. So if you have dopaminergic activity, you might be messing with something down there in the kidneys, right? So you have to be adrenergic receptors all over the body, right? So thinking about the physiology of what might be going on if you hit any of those targets anywhere in the body makes drug discovery tough, but we have a lot of successful therapeutics, right? Okay, are you guys hungry? Thirsty? Take a break. Come back later this afternoon. Somebody else will be teaching. I'm gonna take the afternoon off and not teach. I have to teach tomorrow morning here, and I have 2 morning and afternoon on Friday, so that's gonna be fun, right? Be a lot of talking. I'm going to have a sore throat by the time that's all done. Okay. Anyways, we'll cut off now. I don't know. I was trying to hope, Dr. Deepak, do you know what time we're going to start at?
In the afternoon?
In the afternoon. What time?
Yeah, around
2? So I guess a little bit earlier than you would. We'll start again at 2 p.m. That's the goal? Okay. All right. Cool. 2 p.m. See you all.
Okay, so today afternoon session we have again very interesting talks. So today, like we have two eminent people from our nearby institute from IIT Roped. The first talk will be by Dr. Indranil Chatterjee. Dr. Indranil is currently associate professor at the Department of Chemistry, IIT Roped. Dr. Indranil obtained his BSc from Calcutta University, and then he moved to IIT Kharagpur for his MSc. In 2008, he moved to Germany for his PhD at Westfälsche Wilhelms University Münster. Did I pronounce it correctly? Under the guidance of Professor Dr. Armido Studer, where he studies centered on catalytic asymmetric cycloaddition reactions. After finishing his PhD study in November 2011, he joined as a postdoctoral fellow with Professor Paolo Malchiori in ICIQ, Tarragona, Spain, in March 2012. His area of research mainly focused on new organocatalytic cascade reactions. From 14 to 16, he did another postdoc with Professor Martin Oestrich at the Technical University Berlin, concentrating his research on Lewis acid catalysis. In December 2016, he joined IIT Roped as an assistant professor, and since August, like last year, he is a associate professor at this institute. He also got the Institute Best Teaching Award in 2020, and also got a Theme Chemistry Journal Award 2022. So, sir, both of you, I would like to tell that this GIAN course is like going on since Monday, and we had very interesting talks. Professor Altman has really inspired all of us with his interesting talks on how fluorine moiety is actually becoming very important, for the medicinal chemist. And also we had a few talks about how to build fluorine compounds. Again, a little bit discussions happened already on transition metal based catalysis. I also would like to tell you that we have around 15 master first year MS Pharma medicinal chemistry students. We have few from second year master students. Mostly then we have PhD scholars, few from Punjab University and few from NIPER, and we have 3-4 postdocs also. Okay, so we have the little mixed audience as well. So with this introduction, I would like to invite Dr. Indranil for today's talk. Yeah. Slide changer or something, will you manage? Okay, again, एक्चुअली वो पॉइंटर यहाँ पे चलेगा भी नहीं, इसीलिए हमने रखा नहीं।
जस्ट चेंज करने के लिए इससे कर दो,
इसी से कर लो, क्योंकि वो रिकॉर्ड भी हो जाते हैं।
ओके। हाँ,
आपको चाहिए होगा
पॉइंटर चेंज करने के लिए, थोड़ा मूव करने के लिए चाहिए।
ये है हमारे पास yes.
Yeah, thank you, Dr. Deepak, for the kind invitation, and thank you for giving this opportunity. So what today I will talk about, so we have been going through Ryan's lecture. I think audible, no? It's
No,
fine.
actually we have to record it, so that with this audio will be better. like this is good, but
Yeah, okay, yeah, perfect. Yeah, so what you have been majorly listening from Ryan, probably the nice small molecule, fluorine. So what I will going to talk about the development of the fluorine chemistry, but majorly towards the synthetic area. Okay, so in Roper actually what we have been working, so this is just for Ryan actually, so very close to here, so maybe 40-45 minutes from here, you can reach our IIT Roper, and you see it's close to the Himalayan region, so in a clear sky you can see the Himalayan mountain also, and we have also very nice structure of our entrance gate, and just symbolizing the Harappan civilian. Okay, so ancient Indian civilization. So what we are doing in our laboratory, so we work on photoredox catalysis, we work on Lewis acid and transition metal mediated reactions, and apart from this we also worked on photo-induced transformation, okay, that do not require any photocatalyst or any transition metal. And apart from there, another area we have started the classical Umpolang chemistry. Okay, so what I will going to show about the development of the fluorinated molecules. Okay, so if we want to start the photochemistry, so we know the mother nature is the major photochemist. Okay, no one can beat mother nature. And what actually we are doing basically in the laboratory, we are just in between the mother nature and the technology. Okay, so we are in between doing the photochemical reaction. And if you consider the photochemical reaction, majorly we can divide it into three categories. Okay, so one is the photoredox catalysis, one is the EDA mediated reaction, and the another one is the photo-induced transformation. So I will try to cover all these three areas to show you that what we have developed recently. So this is just a brief introduction of the photoredox catalysis. The photoredox catalysis is that where basically the molecule cannot absorb the light, then you need an extra stimulant. The photocatalyst, it's in favor of the molecule, it can absorb light, goes to the excited state and can do the electron transfer process. Okay, so this electron transfer process, you can clearly see the one electron of the photocatalyst is going to the excited state pi star orbital, and then it can take up electron or it can lose electron. Okay, in that cases it can build up oxidative and reductive quenching cycle. Apart from this, the photocatalyst also involved in energy transfer process. That means it can take up the energy, goes to the excited state and release energy and come back to the ground state. And with that energy, the molecule can be excited. Okay, so after the photocatalyst, the other method is the EDA guided method, where none of the molecule can itself individually absorb light, but when they mix together, they form a complex, and that complex upon excitation can go to the excited state and do the electron transfer process. So in this case, you can see that more or less you have two parts of the molecule. One called the electron donor, that is mainly consists of the electron rich molecule, and the other one electron acceptor, majorly consists of the electron poor molecule. So these are the major part. Then what is the last part is the direct photo excitation, where the molecule can absorb light and itself can go to the excited state and can do the electron transfer process. So in this case, So in this case, you can see all of these compounds, classical compounds, whether it's a benzothiazolene or xanthate salt, these are well-known photoexcited chemistry and well explored. But what I will going to talk about this dihydropyridine derivative, what is known as Hanchester, and its photoexcitation chemistry. Okay, so all these three chemistry I will touch to show you the synthesis of fluorinated molecules. And already you have familiar that why we need fluorinated molecules, whether it's a medicinal chemistry, pharmaceutical, agrochemicals, a part of larger part of the molecules contains fluorine atoms. Okay. But we divided or we targeted a different fluorinated part. We majorly targeted difluorinated molecules. Okay. So if you go to the literature, you will find two kind of difluorinated molecule. One, the upper part is you can synthesize from benzo trilfluoride system via CF bond cleavage, and the lower part you can synthesize from trifluoromethyl ketone. So we actually targeted the difluorinated molecule via CF bond activation. Okay. So with this, why we need actually difluorinated molecule? So it's a very famous quote by Phil Barron actually, that it's basically the CF2 molecule, it's a bioisosteres. It's called the phenomena called the point mutation, where it can replace the methoxy ether. So a simple oxygen, if you replace with a CF2 group, it can insert high metabolic stability. Okay, and you can see from the examples that how change from methoxy to the CF2 molecule can increase the metabolic stability and can affect the IC50 value. Okay. So not only this, even from trifluorinated part to the difluorinated part, if you move, it can change the pK, the lipophilicity, and many other properties of the molecules. Okay. So basically CF2 containing molecules you can synthesize in two ways. The classically, either you add fluorine to the molecule or you detach fluorine to the molecule. So we choose actually this part, the last part, via single CF bond cleavage. And if you go to the single CF bond cleavage, you have again two categories. Either the photoredox chemistry, that means the classical visible light mediated approach, and the other one is the enolate chemistry. So enolate chemistry was one of the oldest chemistry for CF bond activation or for the synthesis of difluorinated molecules. But when we started the chemistry of CF bond activation, this was the totally unknown area in photoredox catalysis. Now why we choose trifluoromethyl ketone? One reason, academic reason, is simple, that the CF bond activation using photoredox catalysis for trifluoromethyl ketone was unknown totally. But our idea was that after the CF bond activation, you can still have the carbonyl group. Okay, so you can easily functionalize the carbonyl group for various synthetic modification, and you can build up a library of fluorinated molecules. And obviously, the redox potential of trifluoromethyl ketone is much lower than the benzo trifluoride system. But definitely, you know, the challenges are there, because the major challenge is how to control the single CF bond activation. First of all, the CF bond activation itself is a challenging part. It's a very strong bond energy, difficult to activate, and then if you are able to activate, the question is how to control the mono activation. The second part is the classical reactivity or single electron transfer of carbonyl compound generally generate the ketyl radical. So the ketyl radical undergoes a spin center shift followed by the fluoride elimination. So in this case, basically the question is how to overcome the ketyl radical reactivity. So as soon as you form the ketyl radical before the spin center shift to form the CF2 radical, the ketyl radical can itself reactive and it can itself undergo reaction. So how to avoid this kind of chemistry? So with this actually we started the area for CF bond activation, and so this was the thing actually initial observation during the COVID time. So we spent almost 6 to 8 months. Okay, either we got exhaustive defluorination that I was talking about, that no control about CF bond activation, or if we can tune some of the properties like temperature, okay, light source, we can obtain a control, but still it is not what we want. So we struggle, we used all kind of reaction possibles, particularly reaction parameters and particularly the solvents. We tried all the solvents, whatever we have in the laboratory, but we are unable to get what we want. So in that time we have HFIP in our lab. So we just started the chemistry using HFIP, so hexafluoroisopropanol, and I remember I told my student, why not you are trying with HFIP? So just it was a trial, and surprisingly we got our desired product. And this is also for the students, you can see the TLC, the left side. It's a classical solvent system, hexane ethyl acetate. We run many times and we see only one spot, and it looks like a starting material. But if we change the solvent in dichloromethane, now you can see classically it's a single spot. It's a complete conversion of the starting material to the desired product. So we screened various parameters, and using this iridium photocatalyst and HFIP and using TMP as a base or a reductant, we can get our desired CF bond activation, and it's a single CF bond activation. Okay, so without photocatalyst, without light, there are no reactivity. Okay, so with this actually we entered the substrate scope, and you can see substrate scope is, I would say, moderate to good, not excellent. And you have example where you can see the examples 3D, where you have the benzotrifluoride system, but instead of benzotrifluoride, the fluorine of the trifluoromethyl ketone is activated. So it's also very selective. So we've also varied the ketone part, and you can use also aliphatic ketone as a substrate. But the more importantly, interestingly, you see what we wanted before, that to functionalize the carbonyls. And you see all the transformation are very classical textbook transformation. Okay, so you can actually do the deacylation process. You can have the CF2H molecule. You can do the simple lithium aluminum hydride reduction. You can see this pyran moiety. You can have the reduction followed by fluorination. You can have this trifluoroethylene compound. Okay, so lot of fluorinated molecules you can build up using the classical carbonyl chemistry. So when this chemistry was done, so the chemistry majorly based on the addition, I will come back to the mechanism later. So the addition of the CF2 radical to the acrylamide system. Then we ask ourselves what will happen to the olefinic system, simple olefinic system, whether it's a activated or unactivated system. So with this actually we started to investigate the reactivity of this CF2 radical with the styrene compounds. And you can see again we face the challenge. We got 3 different products. Okay. So the first trial we got 3 different products, but all the products are very, very interesting. Particularly the interesting is that this THF moiety, difluoro THF moiety, apart from the saturated or unsaturated moiety is also important. So we ask ourselves, can we tune the reaction condition in such a way that we can access all the materials? So this was the target. And shortly, if we use iridium photocatalyst, HFIP in TMP, that is the previous condition, we can get exclusively the tetrahydrofuran moiety. And if we use in presence of trifluoroethanol instead of HFIP, ruthenium photocatalyst and a combination of TMP and Hanchester, you can get the saturated 4A as a major product. Okay. So with this actually we started, and the motivation was the core molecule, the gemcitabine. So this is a blockbuster anti-cancer drug, okay, and our targeted molecule, the product is basically contains the same difluoro tetrahydrofuran core, okay, and we know classically either you can do the electrophilic fluorination from the carbonyl, or you can start with the nucleophilic fluorination. Okay. So we thought about this new methodology to explore the reactivity, and you can see for many kind of activated styrene moiety, we can synthesize this difluoromethylene compound, difluoromethyl group containing tetrahydrofuran moiety, and this is the acetal actually, which is also the part of the HFIP moiety. And this acetal is stable, that you can isolate, you can have the crystal structures, okay. And we explored the scope where not only the internal, the external olefin, so most of them are working, and diastereoselectivity is also very good. Okay, but the unactivated system is not working in this case. That means you need the phenyl group, the styrene moiety. Then we explore the other optimized condition to obtain the saturated moiety, and here you can see in presence of ruthenium photocatalyst, TMP and Hanchester in trifluoroethanol, you can get this saturated difluoromethyl ketone moiety. Okay. So here also I want to mention the reaction is restricted to 1,1 disubstituted olefins. Okay. So what we did basically, we took this tetrahydrofuran core, and if you treat with a Lewis acid, you can get this unsaturated part also. So previously we had 3 structure, now we can achieve all the 3 structure either directly or indirectly. You can do the borohydride reduction and then dust mediated cyclization. Dust is not only for fluorination, but it also can trigger the carbocation formation and then cyclization, and you can see that not only naphthalene, the tetrahydronaphthalene core you can generate with very high diastereoselectivity. We can use naproxen as a drug. We can tag the drug of naproxen to the trifluoromethyl ketone, and we can have the synthesis of this modified this tetrahydrofuran moiety with very high diastereoselectivity. Okay, so I will just briefly discuss the mechanism. So this is a fluorescence quenching process where the fluorescence quenching can give you an idea that which part of the molecule can quench the photocatalyst. That means the catalytic cycle, whether it will start via reductive or oxidative quenching cycle. Okay. So this is the most interesting part. You can see how HFIP is influencing. So you can see in the left hand side the redox potential of trifluoromethyl ketone in acetonitrile, and you see the change, the decrease in the redox potential in HFIP. So HFIP can form strong hydrogen bonding with the trifluoromethyl ketone oxygen, so that its LUMO gets lower and the redox potential also gets down so that you can easily reduce the molecule. So not only this, the HFIP can also form hydrogen bonding with the fluoride so that it can make the carbon-fluorine bond weak. Okay, so with this actually, so this is the mechanism. So you can see the reaction started via the oxidative quenching. So a single electron transfer by the photocatalyst to the ketones, followed by spin center shift fluoride elimination to form this difluoroketone radical. Then what will happen in presence of acrylamide? The radical adds to the olefin, followed by the radical adds to the aromatic system, another single electron transfer, and then aromatization. In case of olefin system, simple olefin system, what will happen? This second single electron transfer can generate benzylic cation. Okay, so stable benzylic cation which was trapped by the ketone itself. Okay, and followed by the formation of oxonium ion, and the excess HFIP is in solvent, although it is less nucleophilic, but its concentration is very high. Okay, so it can trap to the oxonium ion and you can get this tetrahydrofuran containing acetal. And in case of the Hanchester, so Hanchester, what it can do, basically it can quench the radical, the benzylic radical via hydrogen atom transfer. So basically all the cases you see that you can module or you can channelize the product whatever you want by proper designing. Okay. So this Hanchester chemistry, it's a very interesting chemistry, and if you go to the literature, you will see that how this chemistry actually developed. So Hanchester we know is used as an hydride transfer reagent. But if you go to the photochemistry of Hanchester, you will see the Hanchester photochemistry starts very, very long ago. So it was started as a photoreductant, and we know why the Hanchester is important, because it is the NADPH, NADH analogs. Okay. So not only the Hanchester, the NADH itself also used in as a in photochemical reaction. But apart from Hanchester, the 4-alkylated Hanchester was first used as a alkyl transfer reagent. Okay, so this was the work, one of the breakthrough work in 2013, and from that onwards, people jumped into this field to use either in presence of photocatalyst or in presence of transition metal photocatalyst in dual catalysis to explore the reactivity of 4-alkylated Hanchester. And it's a very interesting reactivity, and you can see that you can generate not only your modulated radicals, but you can use this radical under photoexcitation. So what is photoexcitation? So photoexcitation means in ground state. So Hanchester is used as a photoreductant to quench the photocatalyst. Okay. So that means it's a donor electron, moderately electron rich. So it can donate its electron to quench the photocatalyst. So the molecules may be in the ground state are a moderate reductant or oxidant, but it can become a powerful oxidant or reductant upon excitation using visible light. So this photoexcitation chemistry is very, very interesting chemistry, and you can see classically, so this is a 4-alkylated Hanchester, and you see its excited state redox potential is very, very high. And if you see the redox potential of, so this is both the 4-alkylated and also the classical Hanchester, and it's very high compared to the carbonyl compound, particularly the trifluoromethyl ketone. So we did the CF bond activation of trifluoromethyl ketone using photocatalyst. Then we ask ourselves, can we use the photo excitation of Hanchester to activate the carbon fluorine bond? Okay, so this was the idea, and what is the outcome? It can be the transition metal free, it can be photocatalyst free, and more importantly, whenever you have Hanchester, you have two possibilities. Either you transfer the hydrogen atom at the 4 position, or you can modulate the alkylated Hanchester to transfer the alkyl radical. So both the way you can functionalize the molecule. Okay, so we started to investigate the reactivity. So the role of B2Pin2 I did not explain previously. So B2Pin2 is majorly used as a fluoride scavenger. Okay, so the fluoride anion which is living, that can be captured by B2Pin2. So the reaction condition, you can see you need a base. Again, HFIP is the key solvent. Okay, and in presence of B2Pin2, you can basically get the defluorinated alkylation process. Okay, so with this actually we started to have the scope, and here you can see you can vary the ketone part, you can vary various alkylated part. So the primary radical, secondary radical, tertiary radical, even the non-activated radicals you can add, but unfortunately the primary non-activated radicals are not working. So whenever you have, you can also do the late stage functionalization of various molecule, various drug molecules. So we did with ibuprofen, naproxen, even you can use natural products like menthols. Okay. Now whenever you can transfer the alkyl radical, so that I mentioned that you have always a possibility of transfer hydrogen atom. So if you can transfer hydrogen atom, you can get hydro defluorination process, and you can see the reaction time. It's very short reaction time. So if you wait for longer time, okay, so we started from longer time and slowly we optimize to reduce the time. Okay, and if you wait for longer time, you will see the major product is the exhaustive defluorination. But if you quench the reaction, okay, at least half an hour, within half an hour, you can get your mono defluorination product, and you can perform reaction over lot of various trifluoromethyl ketone derivative. Okay, so what we did, now you have two sequence, right? Hydrogen atom transfer or alkyl radical transfer. The question is, can we do sequential things? So the first one, we did alkyl transfer, and then we did hydrogen atom transfer. So now instead of difluoro, you can have a monofluoro compound. And you can use also this difluoroketone for the dust mediated fluorination, so that you can have the tetrafluorinated ethylene compound. Okay. So what we can do? You can do classical reductive amination process. So now this amine, you can see this amine is the starting material of these two receptor and inhibitors. Then you can do simple Wittig reaction, and this is also a starting material or the closest one with this inhibitor. You can do the alcohol reduction, and this alcohol, if you do the esterification, this is also close to a receptor. So we did not went up to this, but we have shown the pathway for new CF bond activation protocol for the synthesis of these starting materials. Okay. So mechanistic things. So what is photo excitation and what the exact things are happening? So photo excitation, you can see if you mix all the component individually and as a mixture, in the UV visible, you will not see any charge transfer band. So the charge transfer band, if you see, it indicates the formation of electron donor acceptor complex. but there is no formation of such electron donor acceptor complex. The fluorescence quenching experiment can give you an idea that the fluorescence is quenched of the ketone is quenched better from the combination of Hanchester and base. So that's mean without base the reaction is also working, but the yields are low. You need the base. So what the base is actually doing? So base is basically interacting with the nitrogen, the NH proton. And you can see from the NMR, the NH proton is gradually shifted. So that's mean it is not completely deprotonated. It is about to deprotonate. So what will happen in this case? You increase the electron density. Okay, you increase the electron density, so which is a donor, now it become a better donor. And electron density increase mean you increase the HOMO of the Hanchester, and the LUMO of the ketone is already decreased in presence of HFIP. Okay, so that actually give you so fast this hydro defluorination process. And you can see this one, just compare. This is the excited state potential of 4 alkylated Hanchester. It is minus 1.36 in acetonitrile, but which is very high in HFIP. So HFIP not only changes the redox potential of ketone, but it also affects the redox potential of excited state redox potential of the Hanchester. So with this actually we propose a mechanism where you can see the combination of base and Hanchester, it actually the main species which actually absorb the light and goes to the excited state, then electron transfer process to form the radical cation, and you generate the CF2 radical. Then the radical cation, so these Hanchesters are pro-aromatic system. So it prone to aromatize. It's ready to aromatize. So during aromatization process, it release the alkyl radical, and both the radical couple to form these alkylated ketones. Okay. So with this actually we move forward, and we found now how we can move from the ketone to other molecules. Okay, by taking the reactivity of Hanchester. So you can see the Hanchester redox potential we already seen. We thought about this ketene, this imine part. So this is the choice of this imine is why we choose this imine, because if you could functionalize this imine, it is an amino acid precursor. Okay, so the simple idea was you can take ketone, amine, you mix, you form in situ imine, you dump Hanchester there. Okay, so what will happen? Hanchester, if it will able to reduce, it will transfer one electron and you form this radical anion species. Okay, now the question is, can we functionalize the C center? If we can functionalize the C center, what you will get? You will get basically quaternary amino acid derivative, and we know how important is quaternary amino acid derivative. There are a lot of molecules, lot of importance at the quaternarization of amino acid. So with this idea actually we started, and here we try to club again another CF bond activation from trifluoromethylated olefins. So the idea was that you generate the C center radical, and then the radical adds to the olefin. The question is, can this vinylic CF3 molecule can be activated? Okay, and you can see now not only you are getting the quaternary amino acid precursor, but you are getting this GEM difluoroolefinic compound. Okay, so with this actually we started to explore the reactivity, and here the reaction conditions are very simple. Okay, you see you have Hanchester, you have base, solvents, light. So, and if I tell you simply, you just mix ketone and amine, you stir it, you know how long you need to form the imine, then you can take the same reaction vessels, or you just take it to the rota, simple aerial condition, you just evaporate the solvent, you take the same vial, you add acetone, you add Hanchester, you add base, and just shine the light, and you will get your desired product. And you know that with this system, you can have ketoesters, you can have amine, you can vary the olefins, so lot of part you can vary and you can explore the scope. And I am not going into the details of the scope, but you can see you can synthesize lot of GEM, difluoroethylene type of compounds. So we explore this one not only for this ketoester, but this reaction also work for benzophenone, also for this diester derived imine, but unfortunately for benzaldehyde and acetophenol, we got very, very less reactivity, because the reaction is a combination of Umpolang chemistry of carbon center of imine as well as a CF bond activation. Okay. So the mechanism, I will go quickly. So it's a radical mechanism. So if you add radical quencher like tempo, you can see you can detect this mass of this compound. One is the tempo adduct and another one is the dimer of the radical species. Okay. Now what is the mechanism? Actually we spent a lot of time, and the referee also asked us to present the work very carefully, because there are two parallel things going on. Okay. So whenever you have an electron donor, electron acceptor, not only photoexcitation is a phenomena, you have a possibility of a charge transfer complex. Okay. The charge transfer complex, you can see the left side, the EDA, it's very slight difference in the charge transfer band. Okay. Because the thing, what I think the reason might be the base is also involved in the EDA complex. The base is an inorganic base which is not properly soluble in organic solvents, and that may affect the EDA. Okay. Then what we did the concentration variation, concentration dependent EDA or UV visible, and you can see clearly if you gradually increase the concentration, the EDA is becoming very strong. Okay. So what we did, we measured the Jobs plot. So Jobs plot is for the EDA complex to determine what is the stoichiometry of the two substrates or maybe the three substrates. Okay. And fluorescence quenching, NMR study. So all this study we actually did to explore the mechanism, but still we think that we need a support of DFT exactly to find out what is going on. Okay. So the DFT calculation, you can see it actually indicates it's not a dimer, it's a trimer complex of EDA. So where you have your donor, which is the Hanchester, imine is the acceptor, and also base is involved, and you have a 1:1:1 trimeric complex. Okay. And if you can go to the right side, extreme right side, you see the predicted wavelength. It is 429 nanometer. We are using 450 nanometer. So it's very close to the blue light region. Okay. So with this actually we propose a mechanism where you can see you form the imine and then you form the charge transfer EDA complex. This complex can excited state, it can go to the excited state and do the electron transfer process. Now after the single electron transfer process, you generate the alpha amino radical. And this alpha amino radical can add to the trifluoromethylated olefins. You generate this benzylic radical, and this radical can accept another single electron to form the carbon ion, and the carbon ion actually triggers the beta fluoride elimination. Okay. So, the last part, it was a different development, but it is also containing a fluorinated part. It was the this again started from this olefinic part, the vinylation part attached to the difluoroketone radical. Okay. So, basically you can get this allylic difluorinated compound. Now, this allylic difluorinated compound you can find in many natural products and drugs molecule. So, we thought actually this kind of disconnection approach, right. Now, the question is, we know how to get the difluoroketone radical, okay. Either CF bond activation, which is a very difficult process, but also you can get simple CBr bond activation. Okay. So, synthetically that is also a logical process. But what we thought about, what about the vinyl group transfer reaction? So, this development is not closely related to the fluorinated fluorine chemistry, but it is a different development. Okay. So, it is the development basically based on the Hanchester part. So, Hanchester part, so far Hanchester is used as an hydride transfer reagent, hydrogen atom transfer reagent, or alkyl transfer reagent. Apart from this, you can have various other group as an R, like you can transfer acyl group, you can transfer amidyl groups. Okay. So, this kind of group you can transfer. Now, the question is, if you consider why these molecules are so nice, because you can easily synthesize this molecule from feedstock aldehyde derivative. You know, it is a classical Hanch pyridine synthesis. If you have the heterocyclic chemistry, you know the Hanch pyridine synthesis, and it was the previous step before the aromatization or oxidation of Hanchester to Hanch pyridine. It is a stable compound, you can synthesize using classical feedstock aldehyde. Now, we thought about, can we synthesize a vinylated group instead of alkyl, a vinyl group at the 4th position using alpha beta unsaturated ketone. Alpha beta unsaturated ketone, you can do aldol reaction, readily you can prepare in gram scale in the laboratory. You take that one, even the crude product, instead of aldehyde, you insert alpha beta unsaturated ketone, you will get this vinylate Hanchester. The question was, can it be transferred? Can it do the vinylation? Because compared to the other process, if you want to do the transfer vinylation, you need to break the sp3 sp2 bond, which is quite challenging. And you see that we started, and what we realized, the core of the Hanchester is very interesting also. So, the classical Hanchester is the ethyl or methyl ester, but if you can synthesize also the cyano derivative, you can synthesize the tertiary butyl also. And if you see the bulky tertiary butyl actually force the carbon-carbon bond breaking, and you can have, using this 2A, you can basically do the transfer vinylation. And this transfer vinylation now coupled with the CF2 radical, you can get allylic difluorinated compound. So, we did this reaction and we found now not the transition metal based photocatalyst, but rather the organic photocatalyst is very important for this reaction. The stereoselectivity is also high, is 8:1, but towards the E olefin. Then we varied, we synthesized this CZIPN, this is an organic photocatalyst. We synthesized various CZIPN in the laboratory, And what we found that, this is also interesting, the 5-CZIPN, you can see the EZ ratio. Now it's reverse. Higher Z compared to higher E. Okay, so we thought about whether we can access by changing the catalyst either E isomer or the Z isomer. So this was, I will come back later, but we optimize the reaction condition, and here I want to mention that we got the best condition if we use Ki as an additive. Okay, so Ki, potassium iodide, you know, it's used as a nucleophilic catalysis, used in the nucleophilic catalysis. So this idea came back to our mind, so that we use potassium iodide, even catalytic amount, and we got very high reactivity. So with this, actually we explored the scope of amide and as well as ester part, and in the amide part you can also include various amino acid derivative. Then we explore the vinyl part, and in the vinyl part only the disubstituted, where in the disubstituted vinyl group you can include the alkyl part. Otherwise, again the unactivated olefin is not working. So the question is, why the unactivated olefin is not working? We struggle for a long time, because if we consider a radical cross coupling mechanism, it should react, but why it is not reacting? Even if we replace a tertiary or secondary radical precursor. Okay, so we scale up the reaction. You can do the reaction in 1 millimole scale. Now you can use, you see that you can use the 5-CZIPN catalyst. You can run the reaction over longer time. Okay, and you can get now the Z selectivity over the E selectivity. So 4-CZIPN you can get E selectivity, 5-CZIPN you can get Z selectivity. So what is happening basically, that you are forming the E product, okay, then the 5-CZIPN is a better energy transfer catalyst. So 5-CZIPN over the longer time, it transfer the energy and you convert the E product to the Z product, and that also we observe via the NMR study. Okay. Now you can functionalize the allylic difluoro compounds, you can do the hydrogenation, you can do the reaction with Grignard, so you can have the ketone also, you can hydrolyze the ester to acids, you can do the reduction, you can do epoxidation, cyclopropanation, you can do lot of functionalization of the olefinic part. So the mechanistic study, you can see the Hanchester is basically quench the excited state of the photocatalyst. Okay. Now, so with this we propose a mechanism where you can see the photocatalyst is quenched by the Hanchester. So you generate this radical cation species, and then the catalytic cycle was closed by transferring one electron to this bromo difluoroketone moiety, so that you can generate this difluoroketone radical. Now the question is whether the radical coupling or the radical addition elimination mechanism. So this was we proposed based on our experiment, that what can happen, this radical can add to the olefin and you form the radicals C and D, where the majority of the radicals remain in the D state, and from there actually you can cleave the carbon-carbon bond and you can have your desired product. Okay. The other mechanism, what is also the classical mechanism, is the radical cross coupling reaction. So yeah, so this one, yeah, somehow I missed actually that slide. No, yeah, I missed that slide. So what we did basically, we took this compound 2p. So it's a radical clock experiment. It's called a radical clock experiment. So if it's the radical addition elimination, then the radical, the benzylic radical next to the cyclopropane ring will open the cyclopropane ring. So we did this experiment and the cyclopropane ring opened and it cyclized with the phenyl part. Okay, but we are unable to isolate that product, but we only have evidence from mass spectroscopy. So with this actually we proposed this mechanism where majorly we thought the radical addition elimination is the major pathway, and that is why you need always the phenyl group, at least one phenyl group, and that is the reason why probably the alkyl, the unactivated olefins are not working. Okay, so with this actually I will conclude. So you can see that you can do the single CF bond activation, which is a challenging part. You can do in presence of photocatalyst, without photocatalyst, and throughout this journey you have seen that how a solvent can affect the whole reactivity, and we call it as a magic solvent. And really lot of people who works on HFIP, although I will not suggest it is not a fully green solvent, it's a toxic solvent, but it can give you many new interesting phenomena. So with this actually I like to end my today's talk. So here are my group. So whatever I present here, I am presenting, that is majorly the work of this excellent student and this talented hardworking student. I am really thankful to all the funding agency, to all my collaborators, and finally to Dr. Deepak for his kind invitation, and thanks to all of you for your kind attention.
It was a really wonderful. I think now we can say that really the light has shined, and because the last 3 days we were discussing about such a strong bond, CF bond, and now the technology has shown that even that bond can be flipped, radical can be generated, and we can do again a wonderful chemistry of that. So any questions?
Sir, the paper that you showed that was the manuscript submitted, there you compared the photoredox and photoredox analysis with the acid nitride as well as HFF. So have you did the control experiment with isopropanol or other fluorinated solvent like
Yeah. We did, yeah. Okay, so always whenever we got the reactivity with HFIP, we always tried all the alcohol solvent. We start from ethanol, isopropanol, trifluoroethanol. So all this series of solvents we try, because we know HFIP is a nice solvent, but it is not eco-friendly. So we try to reduce the amount of HFIP also. And in the
similar trend in case of the trifluoroethanol as like
no, we did not observe the reactivity. HFIP is the best one.
So HFIP, are there differences in weight? So first of all, is it coordinated with chlorinated carbonyl?
Yeah.
Is it acidic enough because protonated
Yeah,
carbonyl?
yeah.
And then are there known differences in rates of reduction as a function of the protonation state or hydrogen bonding state of the?
No, they are, yeah, actually mostly what people did the experimentally, but the theoretical, that's been the how many molecules of HFIP are involved in hydrogen bonding, how the cluster looks like, that is till now it's unexplored. So majorly the hydrogen bonding with either with the carbonyl or the fluorine CF bonds, that is we also took help from Stephen Grimme. So their group did the DFT study, and they only shows this hydrogen bonding interaction, but not in details that how many of HFIP are involved, and how is the clusters looks like?
Yeah, I guess I'm wondering about the rate of reduction.
Mm-hmm.
As
Okay,
as a
okay.
function, as a function of hydrogen bond.
Okay, I got it. Yeah. No, we didn't see, but it's faster.
But I mean, it'd be really tough to study because usually when you do Stern Ulmer, it's the first step, which in your case is oxidation.
Hmm. Hmm.
And then after that step, when you go to the reduction, that's really tough to measure
Yeah.
later on.
Yeah.
Just what's the study to measure the rate of the subsequent stuff, you know?
Hmm.
See if there's a.
I don't know whether from the Sternholmer quenching, I don't know the rate from the slope you can measure it or not. So might be the slope because slope will indicate the rate of the fluorescence quenching rate. So
That's usually the first step. In your case, that's the oxidation of the hot ester.
yeah, no. In case of the photoredox catalysis, the first step is the reduction of the ketone.
Oh, I thought it was
Yeah.
oxidation. Okay.
No, it's a reduction of the ketone.
Maybe that'd be an interesting study.
Yeah, in that way you can do actually, basically.
And you also don't see any HFIP involved in any other reactions. Like this is the major product always, and there's no any other side products or anything because these were like not really.
Uh, Not really. Not really. Yeah.
Because maybe if something else is forming which is responsible for catalysis.
Hmm. No, we did not observe. Not really any other side products. Yeah.
Okay, I think anything else?
Yeah, I can ask one
Yes,
question.
Yeah.
yes, yeah.
Sure.
So it's a very wonderful talk. So in your last radical cross coupling reaction, what makes you think is a radical cross coupling? It's just a radical addition. Since it's radical cross coupling, one has to be persistent radical.
Not really.
But
No,
because
not
it's a
really.
fast reacting species, so it tends to
Yeah.
polymerize and undergoes chemical
Yeah. So
reaction.
the challenge of radical cross coupling is the non-persistent radical.
Yeah.
Yeah. So
in
that was the challenge actually, because CF2 radical, the fluorinated part, I think CF2 or CF3 radicals nature is totally different.
Yeah, they are electrophilic radicals.
You cannot say like direct electrophilic. So you have to go to then Armido's this review. Then you can see it can be electrophilic, it can be nucleophilic. Because if you consider the electrophilic radical, then the question I will ask how it can add to the acrylamide system. Because this was the first question actually Vladimir asked to my student during the postdoc interview. Because it's very difficult to predict the nature of the CF2 molecule, also the fluorinated molecule and also the CF2 radicals.
So they are kind of amphiphilic radicals.
I would say this.
Okay.
So there is one review of Armido Studer in Angewandte. So they majorly described the fluorinated radicals, CF3, CF2 radicals. Yeah.
Go to these slide number 79, please.
Huh?
Slide
Slide number
79.
79.
So many slides. Maybe it was all original.
No, there are a lot of duplicate slides. This one?
I think it's the next, the previous one.
Which one?
No, 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 previous one. No, okay.
Yeah, you can.
Then you told us that in first step you can get rid of the solvent over rotation. But then in reaction condition you involve toluene, and it's really hard to get rid of toluene over rotation. So
Okay. The sequential process. You can change the solvent also. You can change the solvent from toluene to benzene also, although it's carcinogenic, but you can change.
okay, so you observe the same
Yeah, it's not a problem. We tried with the co-solvent also. We found in the co-solvent means toluene or benzene and your acetone, the yields little bit drop down.
While working with toluene, did you observe any other like side products? Because toluene itself can undergo some kind of
No,
CH2
this is
saturation.
toluene we used only for the imine formation. It's a classical reaction, so yeah, we did not observe. So the persistent, non-persistent radical cross-coupling, that is the most challenging. And we are struggling there, and reviewers are giving pain always, asking that why not the non-persistents who are radicals are doing the cross-couplings. You have to do it.
Even my postdoc was, Philip, he didn't like this radical cross
Yeah.
because one has to be a persistent radical.
Yeah,
Otherwise, radicals undergo different kind of a reaction, so they don't react
yeah.
in a way you want it.
Yeah.
Right, I think it was, we just thank Dr. Anjanari. So I invite Dr. Rajkumar also to join. We invited Dr. Vijit. Can we take 15 minutes there, or we take a break after this? Yes. Yeah, come.
Oh, okay, okay.
Yeah, I hear you.
Yeah, thank you. Fine.
Wonderful work. So let me see if we have.
No, এটা খুলে নিন।
Let's continue the next talk, and we take a break after that. I don't know what time before you how soon do we came now to like 30 47. So I think we will take a break after this talk. Is it there? What is the status? Generally after 1 talk, but I think it's not required that immediately. Hey. Is it required?
No?
But after talk we should be. Okay, OS is not yet ready, so I don't know how long it will take.
Then finish it.
Because it's a I forgot to tell him. So I think it might take 15 minutes. Yeah, please. Yeah. Mic off? Mic.
Yeah.
Off. वो भी कर लीजिए। एकदम से
स्टार्टिंग लग जाएगा ना वहाँ पे?
हाँ लग जाएगा।
बहुत नीचे है ना?
है। मस्त वर्क था इंजीनियर का, वेरी नाइस वर्क. इट वाज दैट.
वो पुराना जैसे थोड़ा तो बोलता है.
हाँ, that was also वो लोग एकदम अच्छा हो गया. That is why he got that best teacher, best teacher award also.
Hello, sir. So everybody should register for our RMBC conference. All.
I did already.
But you have only 2 students registered till now. I want 100% registration.
Yes, so we are going to have a very interesting
I forgot to.
symposium. We are doing this since last since 2019. RABMC, it's an advancement in bioorganic and medicinal chemistry. So this will be hosted by IIT Ropar, and Dr. Prabal is taking the lead there. And this will be a very, actually I thought maybe if it is during our GIAN course time or something, maybe we would have requested, because I want to join. So that was here, in fact.
From IIT Ropar. He has been a good friend, and we are a part of AVH local chapter, and we conduct many events. This RABMC also, as he mentioned, we have been holding it together and collectively for the past many years. He had his preliminary training from University of Burdwan. This is in Burdwan, West Bengal. Some of you may know that this university produces excellent organic chemistry people across the country. There are many of them are working in a nice way. I happened to visit that place a couple of times. Then he studied for his PhD from National Chemical Laboratories in Pune, which is a pioneering organization for all sorts of chemical research, chemistry research. Then he went to Germany uh, with a AVH fellowship, which is a very, very prestigious fellowship. I am also a member of that. So it is so prestigious. They will give you, they will, if and when you get selected, they will give fellowship to your wife and as well as children.
not only to the professor. Okay, because they respect family values are more important for a scientist to grow. Okay, this is and he spent time at Purdue University from 2007 to 2009. Did you overlap with Professor Altman? No. Okay. Uh, then then he came back to IIT Ropar in 2010. Since then we are working together. He is an expert in synthetic organic chemistry as well as medicinal chemistry, methodology development, organocatalysis, electroorganic synthesis. Likewise, he has many specializations. And he, till now, he already graduated, 11 PhD students graduated from his lab, and he published excellent research papers and obtained many research grants from government organizations. And now he is awarded with CRSA medal, DST Young Scientist Award, NIH postdoctoral fellowship, and DFG postdoctoral fellowship, and many others. So we welcome Professor Banerjee for his nice lecture on the topic of electricity-driven sustainable synthesis of fluorinated compounds.
So thank you, Professor Bharatan, for his introduction, which was not needed, but it's okay. Because introduction, we are here, we know everybody, and nowadays Google is there, everything can be found out there. And at the outset, I would like to thank Deepak and Professor Ryan also, to invite us here to give a talk. And he told me I have to talk on fluorine chemistry. I told I am not an expert. Then Dr. Indolil was called, and he saw one of our paper on cyclopropane chemistry, where we have added some fluorine to some 5-member ring. Then he told you have to present, but today I am not presenting that work. We are presenting some recent work based on our newly found interest in electroorganic chemistry. It's not that new now, it almost 9 years, we have been 8 years we are working on this area. So today I will be talking 2 works actually of fluorination. One is single fluorination and one is CF3 addition. So before going to that, huh? Yes. Oh नहीं
अच्छा वो स्लाइड चेंज नहीं हो रहा है
नहीं ये नहीं लगा है ना
अच्छा ठीक है
यही मैं ढूंढ रहा था
I thought you wanted okay नीचे वाला दबाना है
हाँ no it's okay
but laser pointer will not work
okay that's okay so today as I told I will be talking 2 words on electrochemical 1,3-oxofluorination and electrochemical ring opening functionalization of ABB, azabicyclobutane. So this we will be talking mostly on electroorganic chemistry. These are modern day sustainable chemistry. All of you know. I will give brief introduction on electroorganic chemistry. What is that? How to do that? And all before going to this. So these are the principles I hope you are aware of. What are green chemistry principles? There should be, I am talking about this renewable feedstocks and efficient energy conversion, less waste generation and recyclability, catalyzed way. These are the things, atom economy, less hazardous things. These are all you must have aware of in present day. And electrochemistry, according to the definition, 9 principles is follows. 3 no, but there are long way to go that electrochemistry can be called a true sustainable chemistry. I will tell later on where I have serious issues with the telling is a real sustainable chemistry, but some more effort needed. We are on the right track. Let's see how it comes. So in our group we have long standing interest that will come later on this strain ring chemistry. In my 15 years individual research career, I have been still working on it, and we have worked almost all these ring extensively, mostly on cyclopropane ring. I like that ring from my PhD days because it's very interesting starting material to work with. It is kinetically stable, but many way we can activate it and many nice chemistry can be done. Then in the same way, epoxide, aziridine, and some work we have done on cyclobutane also, and oxyaziridine we have shown it is oxyaziridine. Can you tell what for oxyaziridine generally used? You have Davis oxyaziridine, and you know what for it has been used. You make a enolate, you add oxyaziridine, you can generate, you can add a oxygen there. But we have proved you can use oxyaziridine. With our things, you can transfer the nitrogen. Oxygen part will go as aldehyde, and nitrogen can be added. So those chemistry we have done. Then we have worked on organocatalysis. Some of our work we have used preliminary. Our starting material was cyclopropane only, cyclopropane monoaldehyde, monocarbonyl, and activate it in organocatalysis way. And just before the COVID time, we have started working closely with our collaborator on medicinal chemistry, mostly on influenza we have started. Then the corona came, some of our molecule we have repurposed, and we got some nice molecule, and we have patented it, and based on that was the time we entered to the medicinal chemistry area. And we got really interested. We got 4 projects out of the recently 2 ICMR grant. We have made a virtual center for virology research where 5 virologists are working, and we are giving chemistry support. One of our collaborator is giving drug design. He is a physicist by training, then a biophysicist. Then he is giving us different type of structural scaffold, target identification, and I am the person who give the molecule, and 5 virologists test it. Its work is going, it is the second year of the center, it is going on. So these are the overall interest I have, our group have, not me. I am just presenting on behalf of them. So today, as I told you, we will be discussing on electroorganic chemistry. So what is this? Electroorganic chemistry. We are doing electrochemistry. We are electrolyzing our organic compound and generating intermediates, and which is giving electron. That is the things. So either we are in electrode, you can a substrate goes, in anode it can be oxidized, in cathode can be reduced, and based on that radical cation or radical anion pieces will generate, and if you can tune your reactivity and substrate identification, we can do many types of reaction. Some of the examples I will give. So why to run? These are the things in the beginning I told. So it generate minimal waste. Here I have a little bit these things. Nowadays we are doing in flow, because here the problem is organic compounds and solvents. Organic solvent normally is not conductive. So we have to add electrolytes. So the less waste means if there is no recyclability, so that's what if we do in now flow, that requirement is less. But every reaction you cannot do in flow, there are many other problems. And reagents means we are using electrons as a reagent. Either we are giving electron or taking electron, it's a clean reagent. But the process we are using many other things, and it is tunable. So you can change the potential. I will show you the simple changing the current, how a whole process can be changed. Okay. So just changing the current or potential, what the mode you are doing, you can tune the reactivity. If your molecule has different site which can be oxidized or reduced, based on the tunability of the potential, reactivity of your molecule can be changed. Okay. We will give example. And reactions we are running in milliamperes of currents. So normally these oxidative or reductive conditions are very mild. We are not using very harsh oxidize and all. So how to do it? So this is the typical setup. What in laboratory condition we can make. Take a flask, add your compound, solvent, electrolyte, put 2 electrodes, and give current, and it will get electrolyzed. So what we are talking about, one cathode, one anode, and thing is we need some solvent. Generally, mostly these are less conductive, so we add some supporting electrolyte. Then we stir it for homogeneity, and it will decrease the resistance, and we can add additive. What are the additive? So electrolysis without additive is a surface phenomenon. Your compound has to go to the electrode surface, it should have some diffusion time, then electron transfer should happen. So all of your molecule might not have proper diffusion things. We can use some mediator which has known electron transfer ability from the surface, and that mediator on the way do the job what you want. So that is called, that additive can be added, okay, that mediator. And these are the two things we have, current and potential. Current controls the movement of electrons, and potential energy associated with the electrons. Both are, it is not like that, two different things, both are dependent. Normally how we do the reaction, we use a simple, these are the left hand side one is our made, the way we now doing, and this is the commercially available. You all must be aware that Professor Baran came with this electrocene. The problem is there are many limitations, but that has made organic chemist was fearful to do electrochemistry due to all these things requirement. What it does, it made organic chemistry chemists to do electrochemistry. It is a compact system. You can just add it, there are everything available, you just put it there, switch it on, you can see, take a CV, everything. It's a very compact thing. So that has made electrochemistry more popular, that's for sure. But it's very expensive to run because all electrodes you have to buy from them, attachments, so many things. So to do real chemistry, you have to do yourself, you have to generate your own setup. So you learn from it and use it. So we have made now our way. The left hand side one you can see, that's the way we run a reaction in an undivided cell. So undivided cell means your cathode and anode together, but some cases you have to run the reaction in divided cell. There should be a membrane. So membrane normally we use G4 or G3 frit, and any other membrane, Kinaphion and other things can be used, but we use normally G4 things. So one is cathode, one is anode. Anode you can do oxidize. We have to prove if your reaction is going by oxidation way, you have to put your reaction mixture in anodic chamber, and you have to show that your reaction is happening in anodic chamber only. So we'll give some example, things will be more clear to you. So as I told, current and potential, see, you have to start from somewhere. You take a CV and you have some idea where your compound will get oxidized or reduced. So that voltage you have to provide, according to you calculate how much current you need. So that much voltage has to come, then only there will be some electron transfer. So the best way, this is the very most common way, you take, according to you measure the current and you set the current. These are the things we use nowadays. So this is DC power generator. So there are in this there are 4 channels, 8 channels, mean 4 reaction can be set, and 4 channels are 4 different controller. So if you give CV mode or CM mode, that constant current mode, you set the current, accordingly it will check the voltage. You can see how much voltage you need for your compound to get the reaction you would like to do. So based on that you set and see the potential will slowly increase. So you have to see your potential should not reach such a place that is a decomposition in your compound or electrode get deteriorated. There will be passivation and all you have to taken care of, but here your concentration of the your reactant will decrease. Okay. So another way we can do is fix the voltage. Some point of time you are giving a current, your potential is increasing. So you fix the upper potential, that much you want. The problem with this is sometime you will see your current is 0. So you have to have a balance. When you do it, you will learn all these things. So, here also the current decrease, your concentration of the product should decrease if there is no passivation and other things happening in your reaction. So, these are some, as I told you can do direct electrolysis or you can add a mediator. As I told, it is a surface phenomenon. So, if your compound is not properly getting oxidized or reduced, you can add a mediator like ferrocene or tempo or something that will undergo the oxidation reduction cycle and that will oxidize or reduce your compound. Okay? So, it is a mediated process. So, it can be parallel. See, in a targeted oxidation, your working electrode is anode, you want to oxidize something, there is no oxidation without a reduction. There is no reduction without a oxidation. So, we can use the, that means you can do paired process. One of the substrate might get oxidized at anode and another substrate may get reduced at cathode. So, you can use parallel electricity, substrate 1 can give one product, substrate 2 in cathode reduced reduction can give two products. It is very, very challenging to do, but can be done. And another thing, same substrate can get oxidized, this is divergent paired electrolysis, can give two products. Theoretically it should be, but for that tunability and all is very important. So, as I told, electrochemistry is not the process, it is very new. Organic chemists took it as a toolkit that may be little bit new, but if you go to the history, Volta Pi was invented at 1800th century. So, that means long back. So, after that first organic Kolbe electrolysis and Faraday electrolysis reported at a 19th century beginning. Then beginning of the 20th century these are groundbreaking reactions. There are many other development, we are just giving some of the groundbreaking discovery happened in between. So, you see these reaction Kolbe electrolysis, Faraday electrolysis, these are still relevant. You see about the what according to me electrolysis, you see the population of this world has increased like anything. In India, if you talk about when we are young, population was around 40-50 crores. Now we are 140 crores. But the land has not increased, okay. We have the same land to cultivate to produce our food. But you require nitrogen available in your soil has to be enriched. Then only that is a cyclic process. The nitrogen will go to the plant and that way it will go to our food, our body will generate amino acid, protein, we will live. So, if you talk about the discovery which is sustaining a modern world is the discovery of ammonia synthesis. That ammonia synthesis make us to make urea, that urea our farmers are giving to our soil, that nitrogen coming to your plant and growing food that we are eating and we are producing people and our world is getting populated. Okay. So, that ammonia synthesis commercial process is the electrolysis process. Still now, and that is highly electron demanding process, energy demanding process. Still if you can come up with a technology which will give the energy requirement down with the new electrocatalyst or electrodes or any modification, I am damn sure you will get a Nobel Prize next day if it is commercialized. Okay, so much demand. So, thing is the sono oxidation, if you see nowadays the paper for electrochemistry, still many papers are coming on sono oxidation, oxida oxidation. This is nothing but iminium cation generation followed by nucleophilic trapping. You can do it other way, there are many other methods, but electrolysis give you to do this reaction very easily. Then chain produce this, then I will come to the fluorination process. So, fluorination using electrochemistry, you see it has become popular after 2000. Now you see in 2014 to 21 I have given 7 examples what I have taken. There are many other examples. The electrochemical fluorination is becoming popular, either nucleophile, mostly nucleophilic or electrophilic. This electrophore one, this F last 4, then if you use GT3HF, it is anionic fluorination. Okay. Why this has happened? Because between these 2002 and 14, electrocene came into the market. Okay, and after that people started using it and experimenting it. So we came to this business around 2017-18 when one of my PhD student who has published this ChemCom paper that Devarsi came and he joined because our electrochemistry started from the urea derivative. So that we are doing some urea mediated ring opening of cyclopropane, and we have published that paper, and that time he joined and he has some prior experience of electrochemistry. Then I gave him to do this, then he come up with some idea, and that was the starting point. We have started in 18 that we could publish in ChemCom that point of time. Then this work, I'll come later on, this work he only did, Devarsi, that he came back to our chemistry, cyclopropane ring opening. Unfortunately, this paper got clashed with another guy's paper, we could publish there. Then we have many things we have done. One of the notable thing, when we have three verticals mostly for electrochemistry, we do aryl activation, we do intermediate generation like ketene, azomethanylate, and all these things. Another ring opening remain in our core to do. So in between we keep on publishing work on ring opening using cation aryl radical activation. In this case, this paper, that generation of paracetamol in single step from phenol. What is the commercial process of paracetamol synthesis? You have to start from phenol, you have to do nitration, reduce to amino alcohol, then acetylation. So the nitration, the source of nitrogen here we have proved is from the acetonitrile. One step, but problem still here we are not able to scale up in the batch processes. So we have shown up to gram. We are now working on flow. Hopefully one day we will come up with same way we have shown other things, and other activation and other intermediate generation using electrochemistry. So as I told, cyclopropane chemistry, I like cyclopropane because of this strain ring. It's a little bit for your the student thinks cyclopropane bond angle is 90 degree, 60 degree. So it is very deviating its bond angle from 109 degree. But it's a Coulson-Motive model told that the interorbital angle is not 160 degree. It is 104 degree. Because that bonds are outside. So the surface is electron rich. So that make this compound, the cyclopropane, kinetically inert. So to have a reactivity, we need to have different protocols to activate it, to do it, do the proper reaction. So one of that things was donor acceptor cyclopropane, or we have come up with use aldehyde. Then we have done many chemistry. What I would like to tell, so the activation mode was, the first two was very well studied. Either you use a Lewis acid or Bronsted acid, or you can Bronsted at this case you can make iminium also using organocatalysis, we can activate. But that electron transfer way, so that's what I am telling, the iminium electron transfer way, what is mostly known is oxidizing the aryl ring, means make radical cation there. And electroorganic chemistry, we can do both. Either we can do oxidize the same things, make aryl radical cation, or we can make a n-centered radical, or if I using a cyclopropene means type of things, we can oxidize the double bond, or we can reduce. So we are not discussing today, we are doing extensive chemistry nowadays on carbonyl reduction, means make ketyl radical anion and open the ring and generate the reactivity. So today what are the work today I will be discussing for cyclopropane ring opening is using oxidizing the aryl ring, generating aryl radical cation. So it is not the first things. If you see the photochemistry, they made these things long before, and before that if you go to the original book for Turo, there is the report, the cyclopropane ring activation using electrochemistry. That paper I could not open, but that was known that point of time. They could not study whole. So later on, the selector 4 mediated fluorination is also known. I will quickly go through because of this. Then these are all through aryl ring activation. I will come to the mechanism. Later on, this oxochlorination, oxoamination. Then this paper is very interesting paper. We would wanted to do the work I will present here today, that we could done oxofluorination, but we could not trap see this particular difluorination is very interesting reaction, and their fluorine see normally fluorine added at the last carbon, means this is not working is a problem. So this part, see fluorine, this fluorine is coming there. That was a interesting reaction, because if you could activate the aryl ring, generate a radical cation, then nucleophilic SN2 type ring opening will give a fluorine at the less substituted carbon. But generating another, giving another fluorine at the benzylic position is challenging. They could achieve it. We will come to our work, what we could achieve, and why this paper is important. We have started first work on donor acceptor cyclopropane aryl activation, and whenever we are doing the reaction, the setting up a very inert reaction using electrochemical setup what we have is very challenging. Because if there is little bit of oxygen present somewhere in that cell, or we can bubble ammonia, nitrogen, argon saturated it, all the time we are getting this product. The nucleophile or the dichlorophyll, whatever we wanted to achieve a 3+2 cycloaddition reaction overall. If donor acceptor cyclopropane chemistry, we wanted to have a different regioselectivity. So, but all the time we are getting this, we are working on it to make it happen a paper. By that time our close friend Daniel could publish it, and after that we published this work. Then this is the, what I am telling, this is photo that I will not tell. These two are similar, because this particular substrate we will be talking about the ring opening of difluorocyclopropane. So difluorocyclopropane, there are many reports known if you use metal catalyst, palladium or other metal catalysts. Two groups work extensively and to make different fluorinated compound. Defluorination also known from there, and other thing. We wanted to add a extra fluorine here. We want, could I make what we wanted to do? We see they have done here, if you can see, they could make another fluorine using their own photoredox chemistry. We wanted to use electrochemistry to have another nucleophilic fluorination of difluorocyclopropane. That was our, and at the same time we want that at other position we will put a suitable nucleophile group. So why this is important? So nucleophilic fluorination means you are using triethylamine HF. That fluorine may be an isotopic fluorine. So if we can add it, this F18 fluorine, that has been used extensively for radio imaging. So single fluorination, I think he must have discussed till now from the different thing why single fluorination is, and benzylic position the nucleophile we want. So we can make fluorine single fluorination compound with the nucleophile whatever we want to make a 1,3 bifunctionalization type molecule from difluorocyclopropane. That was the idea. Then when we do the reaction all the time, as I told, the electrochemical reaction we cannot make, still now we could not make it oxygen free with our setup. So whenever we are doing the reaction, this reaction, it is giving these radical things, because we could trap the radical with some radical trapping experiments, then it is getting the oxygen from the moisture and it is forming 1,3-oxofluorinated product. These are interesting compound because this type of things are present in different type of medicinally important compound. We could standardize the reaction, different solvent, electrode. We have varied. I am not going through it. We found if we use carbon nickel, carbon as anode and nickel as cathode, and these are the different electrolyte you have to scan. Then we found that this particular tetrabutyl ammonium acetate, you should ask me why these tetrabutyl things are you are using. This is tetra alkyl ammonium cations are large organic cation, and with counter anion this can behave as a good organic electrolyte. Okay. So, there are sodium perchlorate, sodium chloride, those are inorganic electrolytes. The controlling those things are difficult, but tetrabutyl ammonium salts are good for organic compounds. Okay. There are many other inorganic things I told. We have also used lithium perchlorate, sodium perchlorate. Those are more greener compared to this and less expensive. That is more important. Okay. So, we could standardize it and made several entries, but it did not work with this electron withdrawing one. We could make several entries, we could prove the structures, and one thing is important, you see, you tell me the left hand side example. There are this is the product. Starting material had many cyclopropane. See dichlorocyclopropane, because we have taken nerol, we have added this from the benzylic compound, there was a cyclopropane. Here was the cyclopropane, dichlorocyclopropane. Here was the cyclopropane, if that red color, here was the cyclopropane, and there are other two cyclopropane. If we do our method, only the benzylic one, this cyclopropane opens. These are not benzylic, these remain intact. Okay. So, this compound is having 7 fluorine atoms, okay, and 1 fluorine atom we are adding selectively. We could not take another the radioactive F minus source, and we could not do it, but it could have been very interesting if we could do. So, we have attached different groups and all, we have shown this works. We could vary the cyclopropane other position, because this was one was CH2, we have managed to give other monomethyl, dimethyl, or putting a propyl group, these things works. But with electron withdrawing group, when we put a ethyl CO2 ET group, that method did not work. Then we have proved the reaction. It is when we are taking the doing the reaction in a divided cell and putting our reaction mixture in the anodic chamber, then only reaction happen. If it is in the cathodic chamber, no reaction. So, that means this reaction works via anodic oxidation, only by oxidative process. Means, and the oxidation, aryl oxidation it forms, and we could trap the radical, as I told, we could not isolate. We wanted to do this type of chemistry, but somehow we could, if we add, what is this reaction, how acetonitrile is giving this COCH3? This is the name reaction, it is a Ritter type reaction. Our paracetamol work is based on Ritter type of reaction. Acetonitrile, the nitrogen get trapped, then it form iminium type and water comes and it give these things. Okay. So, this we could do. Why I am telling here this is, you see it, if you see the CV, when it is electron rich, paramethoxy 1, you see the catalytic current, the red one. So, anyway, the red one you see the red one, this catalytic current is red one is for this 1D, which is electron rich, and simple the blue one where there is no electron. You see this get oxidized little bit less potential compared to the blue one. So, its oxidation potential is here. So, this react faster and yield is also good, and this based on this CB and other known things, we propose the mechanism to be like this. So, one electron oxidation, radical cation and radical cation reorganize, and then now you see this is a donor acceptor type cyclopropane, where this is activated, that is a positive charge, F minus attack, ring open, then the benzylic radical form. So, it can then trap oxygen and it get further oxidized to give 1,3-oxofluorinated product. This particular compound we have done many post synthetic application, and we have done one pot application. We made the fluorocyclopropane, and without isolation we did electrochemistry to make yield little bit compromise, but in gram scale when we do, we got around 50%. That is the way we have done the reaction. In a 2-neck flux, one net we put one electrode, another neck another electrode, and we electrolyze it, and we got around 50% product. And this last one, this is very interesting reaction. You see, we take oxofluorinated product, then we treated with this hydrochloride thing, and we got 2 nitrogen that in fluorination product in almost 60% yield. So this is interesting compound. So overall, we have shown to you that electrochemical nucleophilic fluorination, and we have done many substrate scope, and we show the extreme selectivity with having 3 cyclopropane ring in the substrate. Only the benzylic one is selectively fluorinated, and we have done late stage functionalization and other things to show the applicability. Now we are discussing this nitrogen compound containing compound. I did not to tell you, the NIPAR student, most of the drug 82% contain the nitrogen heterocycles, 3% contain multiple nitrogen atoms, and there are different types of rings, and all these are all available in the medchem paper, you can see. So nitrogen compound containing ring size nitrogen in the ring is according heterocycles are very important. So what was our idea? If you are following the literature in modern days, you will see that ABB, this ring opening of aza bicyclobutane or simple bicyclobutane are of interest, because that is giving different bioisostatic structural scaffold in very easily. Okay. We have taken, because ABB to try electrochemical oxidation, because it is having a nitrogen atom, we can oxidize it, and we can do ring opening chemistry of ABB. So, so that was our idea. So that ring opening we wanted to do a cycloaddition chemistry, but if it give a simple ring opening chemistry also, it will give a azitatine ring containing compound. That was the idea. That means we are talking about this ring. So this ring, most studied one is this, putting a aryl ring. But this we could not make sufficiently pure this compound to try electrochemistry. So with little bit we have, see, this is known in the literature, we could not distill it properly. So that was our issue. So we dropped the idea, we slightly modified it. We put a alkene, a tunable handle, and you see there are 2 sites now which can undergo a oxidation. There is a olefin, I can tell 3, there is a aryl group also, and a nitrogen atom. So these all the 3 things can undergo oxidation, and if we can do selective electron transfer in anode, we can have a challenging chemistry may come up from this study. So that was our idea, to see either radical addition or activation ring opening, we can make different type of azitatine skeleton. Now what is bioisoster? Sir also told what is bioisoster. It is what it is tell, nearly equal, it should be nearly equal molecular shapes and volume, approximately similar electron distribution, exhibit similar physical and chemical properties, similar biological activity, and similar target. So what I am telling nowadays, for bioisoster, there is a piperidine. Piperidine can be replaced by azetidine, or if you have a pyrrolidine, it can be replaced by a azetidine. So, these are bioisostatic substitution, and this might give a better activity of your targeted compound. So, that may give give greater selectivity, less side effect, it can decrease the toxicity, improve pharmacokinetics, increase stability, and also might simplify the synthesis, but for this azetidine, this I might not tell, making a 4-member nitrogen containing compound would be more challenging compared to the 6 or 5, but that part is different for azetidine. So, there are different compound with having different functionalized azetidine and fluorination, fluorinated compound. I will come the azetidine, this ABB chemistry, what is known. There are 1 or 2 more paper has appeared, but 3-4 paper I have taken. Either you can do this Suzuki type cross coupling reaction to open. You see all the cases you need a box to protect the NH. So, it goes through this type of intermediate, or you can use a N-center radical to open it to give this azetidine ring formation. This Professor Baran has come up with very nice electrochemical approach to open the make this type of compound, not from azetidine, I am telling here from the corresponding bromo, but this work you see Baran's work. So, he could make method A or method B. I have given the things what they have used, nucleophilic ring opening followed by Bock protection. So, method A they have used simple Bock protection, activate their nitrogen, and nucleophilic nucleophile can attack. Another place they use a triplic acid, a Bronsted acid to activate the nitrogen, nucleophilic ring opening to make the different type of product. But what was our these are CF3 containing drugs. I have given a just distribution from this. There are many compound present days FDA approved drugs also contain many fluorine. This one is CF3 containing drugs. So, if we talk about fluorination, CF3 insertion using electrochemistry, this is the process using simple Bronsted acid. Means you are generating the activating the OH group, generating the cation, then radical, then allylic shift, and SO2 CF3. This is the only example I found where CF3 with SO2 is getting inserted. All the cases, this is called Langlois reagent. It is known to give you CF3 radical. SO2 group goes and it generates CF3 radical. But this one only I found where CF3 SO2 in double bond addition, it is the activated type of allylic double bond. The SO2 CF3 has incorporated. Why I am talking about this, I will come later. So, rest of the things for electrolysis from Langlois reagent to give CF3 radical is well studied. There are couple of papers. What was our idea? We are taking this our modified ABB as a bicyclobutane, take Langlois reagent, electrolyze it. That electrolysis can generate CF3 radicals from the Langlois reagent, and that can attack to the allylic position, opening the ring. I am talking about the product number 2 here, and that NH can be Bock protected. And another one, these things, Langlois reagent will remain intact. It can behave as a nucleophile. It will generate this species OSO2CF3 in the azetidine ring, and it can undergo a 3-3 shift or a stepwise manner. Then now you see attachment is with oxygen, there might be with sulfur. So, all these product possibilities are there. So, this work when we start, we have started from their CV and all 3.5 ampere of current, and we used different electrolyte and different electrodes. Then we found, you see 2A is the product where Langlois reagent generating the CF3 radical, and that is attacking to the double bond, and there is a shift of double bond, N radical oxidation, then NH formation, and it is getting Bock protected. And another one is Langlois N is getting activated, radical cation, and this Langlois reagent behaving like a nucleophile and opening the ring. So, what I am talking about 2OA selectivity. So, we are getting all the product. You see 2A is our CF3 radical generated product, 3A and 4A is from the ring opening first by Langlois reagent by nucleophile lily-CoA, and rearrangement another one. So, we are getting different product in, and the yield was good in carbon nickel 35%, and if we change the electrolyte to tetrabutyl ammonium perchlorate, yield was around 50%. So, we have taken this condition to further study and increase the yield of 2A. That was our first target. So, we have done different experiments and all. We found out acetonitrile DCM 3:1 ratio. If 3 hour time it gives around 60% yield of the 2A, and very trace amount, and please remember the applied current here is 3.5 milliampere. Okay. So, we are getting 60% of the product where CF3 is getting added to the allylic position, and we rest of the ring open product. Then taking this as a things, we have made different substrate. We have varied. Yield was around 60%, 50 to 60%. We made different compound, and you see this last compound is very interesting. But if that double bond is substituted with the methyl, this reaction didn't go with this condition. Now, I have talked about another two compound, that is OSO-CF3 insertion and SO2-CF3 insertion at the terminal position of the double bond. So, to get these two products 3A and 4A, we started optimizing. What? From the CV, I will come from the CV. CV tells that nitrogen center getting oxidized around 1.2 volt, and that Langlois reagent getting oxidized around 1.5 to 1.6 volt. So, that means we have a 0.3 to 0.4 volt window where we can try and get the selectivity. So, that is what we have 1.5 milliampere we have reduced the current, that we are working now in lower voltage. So, in that case we can have a nitrogen lone pair get oxidized to radical amine radical cation, and there the ring opening can happen from the Langlois reagent. So, with that thing is mind, we have started optimizing it, and we found we have changed the see that when you are talking about a different type of oxidation, center oxidation, different current and other thing, you have to do many other optimization, not only the current, your electrolyte, everything has to be changed. So, we found in tetraethyl ammonium perphosphate, the phosphate PF6, in acetonitrile, no DCM, it gives 82% yield of the product 4A. And we also got 3A, that when we are treating with keeping some more time, 3A it is getting long time, 3A is getting transferred to 4A. That part we know. So, we have done a separate experiment. So, if we are adding benzoyl peroxide or other things, it's this, you see the 4A can give 2A, means just simple removal of SO2 can give CF3. That also we have tried. We have taken 3A. 3A you treat with, we have isolated 3A, and taking isolated 3A, if you stir it in acetonitrile, THA, methanol for some time, you see in acetonitrile if you stir for longer time, 5 days, then your 3A get transferred to 4A. 4A means 3A means this is getting 3 type of rearrangement. I will come to the mechanisms that okay, it will giving that product. Now this one, if we are using radical generator benzoyl peroxide and all, so it is going all the way to 2A. That is the original product what we are getting from addition of CF3. So that means you have a control to get directly CF3, you can get OSO2 CF3 thing here, OSO CF3, or you can generate a SO2 CF3 there. So everything you can get. So this one we have taken to make the 4A more. So we have done different substitution what we have shown for the earlier studies. Here yields are good compared to the first one, because there are many other we are working in little bit higher potential. So many other side reaction was happening. Here we are working in 2.1 millivolts, so potential is less. So we are getting good selectivity. So we have shown we could trap with BHT, and another adduct we could trap in BHT that I have not shown here. Acetonitrile, in this condition acetonitrile is getting trapped with BHT. That means CH2, even if you use CD3CN also, we could trap that BHT plus CD2CN. Why I am telling acetonitrile here is behaving as a H dot giving things to the substrate. And we have done this reaction in standard condition in anodic chamber. Only this reaction give around 70% yield. In cathodic chamber no reaction was observed. So this reaction is going by anodic oxidation only. So this for your he told you, did you put any NMR? So this I have taken this 2-3 structure I have taken from the paper. In our paper what we have given, because my word was not allowing me to copy from there somehow, because there is a larger scheme. I put it on the PDF, and PDF we have just taken the picture. So here you see this product, that CH2 hydrogen was coming around 4.3. When there is oxygen OSO-CF3 addition I was telling, here you see the double bond peaks we can see around 5.7 and 6.2. Similarly in carbon, you see in carbon CH2 is coming at 51, but when it is oxygen the center is generating, here it is coming at 84. So we have one of the crystal data also this, but for the NMR how to know where your substrate is, I just put this one. This is the CB. You see the tertiary nitrogen oxidation potential. This we are talking about microampere. See the oxidation potential of this is around 1.2 or less than 1.1 volt. But Langlois reagent you see is around 1.5 volt. Here Langlois reagent you see the current is in milliampere, not microampere, because it gives why it is very high. I will come very next slide. Now I told in 2 milliampere of current we are getting nitrogen is getting oxidized to get nitrogen radical cation, and nucleophilic ring opening is happening. When we are reaching to 3.5 milliampere, the overall working voltage is high. In that voltage your Langlois reagent is getting oxidized. But at that voltage your nitrogen also can get oxidized, because it is below. As the electrochemistry talks about, if you have two things which is having lower potential will get oxidized fast. But then why in higher potential we are getting Langlois reagent to generate the CF3 radical faster? From the it is from the current diffusion current density. Means two reagents you are having which is having larger diffusion current, it will get oxidized fast. but that we can tell, but we have to validate it by data. For that we have done some experiment. Again, this experiment I have taken from our paper. Here it tells, this, there are equations available. You see, we have to done, CB in different scan rate. So where you will see the steep increase, you see steep increase of this is for language reagent. So this slope is more, means your diffusion coefficient for that particular reagent is high. If you see for, this is for language reagent, this is 1A is our starting material. So for 1A remain flats. So we have data from this data. So this is the data we wanted to get. This is for language reagent and this is for our starting material. So it is very high. Diffusion coefficient is very low for our substrate, and diffusion coefficient for CF3Na is 10,000 or 1 lakh time higher than that of our starting material. So if both are there, it is reaching to the potential where the language can oxidize, it will oxidize by kinetic reason. Okay. So that we have formed, based on all these data, we have proposed the mechanism. For one mechanism is very easy. This one for the CF3 radical generation, it will generate the CF3 radical, then it will add, then it will get N dot, and this is from where H dot is coming, for it is coming from acetonitrile that I told, because we have done an experiment, we could prove CD3CN radical we can trap with, can be trapped with BST, that HRMS we got, that is the only evidence we have. And there are some literature precedents very recently came, they are also showing like this. So rest of the things, if you ask me the question, we don't have other data. Okay. So then it is getting Bock protectant giving this product. But other way, where we are working in lower current, the nitrogen is getting oxidized, it is forming radical cation. Then Langlois reagent behaving as a nucleophile here, this ring opening is happening, then again similar process, and we could get this product. Means not get by confirmed by HRMS, then Bock protection is giving this. And another way, 1,3-sulfone rearrangement, it can be concerted, but we from the evidence and literature report, it goes through, might go by a stepwise manner to give the terminal SO2 CF3 substituted product. Now if you treat with radical initiator, it SO2 goes away and CF3 get attached and give the product to A. Okay. So we have done this reaction in gram scale. For SO2 CF3's case, we got 68% product. For CF3 case, we got this thing 51%. We done Bock deep protections, and we have confirmed it by NMR. Then we have coupled with this NH, we have coupled with epmoglycine. Then we could couple ibuprofen, we could couple anti-inflammatory drug, naproxen, and we could also couple olaparib, because this might gives, we have no data to prove what type of activity it could show, but it is attached with the scaffold containing a agitatine ring and fluorine. So better activity might be expressed. So what I have shown, this particular thing depend on standard reaction condition and lower potential and other things, it gives this product. If we use higher potential and this condition, it gives CF3 containing product. So we got 58% yield, and this is the first report of electrochemical activation of ABB, and we play with the potential to get different current, different tuned way to get different other product. We could attach different 3 drugs molecule to the moiety we have synthesized. This biological study might be interesting, we do not know. So based on all the things, what about the work I have presented? I have presented 2 people work. One is that this photo Siddharth is there. So, the left hand side one Siddharth and the yellow things is Nilam. Both this work, first work was done by Siddharth and second by Nilam, and rest of the students and funding agency I would like to acknowledge, and whatever the work done by them, I am here to present their work. So, all the chairs should be for them. Any question you can ask me, and I would like to thank you all for your kind attention.
Thank you, Professor Banerjee. I think it was again, we can say that after standing up live, then we have seen the electrochemical application of again very pure compound. Also, you have shown various other applications as well. But again, it was quite relevant to our theme of the workshop, and I really thank Professor Banerjee for this very interesting chemistry. So, any questions?
This is our department. I would like you to come on 29th and visit.
29th November we have one symposium which we do here.
My lab is somewhere here. This is our lab. Okay.
All watching for the talk.
So can you please go to the slide that where optimization table was shown and 3 products was there? Sir, could you can we say that 3A and 4A product?
3A is forming fast, we have proved. 3A, if you start for more time, it generates 4A. And 4A, you generate T2 with benzoyl peroxide, it generates 2A.
Right. So even if we will not provide the electric current,
No, this reaction doesn't work.
because the ring is very much strange that
This is a stable, it doesn't work.
nucleophilic addition. And one more question is that when addition is happening on reaction is happening on that other side ring, the oxygen is taking part, right? But when the double bond olefin addition is happening on olefin carbon, then sulfur is showing that.
So that's what this may be a concerted process. I have given the mechanism. No, it might be a concerted process, but we found a literature where they are showing like this. We have not proved it whether it is. That's what we have given the mechanism thing and all. So if it can be a 3-3, it may be a sigmatopic rearrangement. No, it may be a 3-3 sigmatopic rearrangement. 3-2 sigmatopic rearrangement. Yes.
So what drives the difference in rate at which or diffusion coefficient? So when you have the
Langlois, yeah.
getting oxidized systematically faster, is it because of the size of the reagent?
Might be for the size, yeah.
Or is it more charged? You have a charged plate.
That is very difficult to tell. Yeah.
Ionic interactions really speeding up.
Yeah. That might be the reason. That the size and charge separation, small molecule may be going diffuse more rapidly compared to the bigger ring. That might be the reason.
There's curious if there's studies in general, anions tend to
Yeah.
way faster coefficient.
But you have to give the paper may goes to an electrochemist. You have to give proper data. So I have to learn all these things to do this, to validify these things. That's what from the catalytic current also you can tell. If you see the catalytic current for Langlois is very high, but that's not quantity that you can quantify that. Next time, or I take more time. कितना लिया time? 1 घंटा. अच्छा, तो ठीक. Thank you. ये रख देते हैं भाई. I don't know. Mic should be there. Mic बंद कर दो भाई.